thanks so much to the audience for being here. And most importantly, thanks so much for the organizer for being flexible to put me in this sensible talk time in my time in the East Coast of the US, which is in the morning rather than in the middle of the night. So I really appreciate that. And it's a great pleasure to be at this conference. My name is Keigo Fukumura from James Madison University in Virginia. So in this talk, I'd like to celebrate the 10th anniversary of NuSTAR by sharing a little bit of our recent ongoing work on actually I changed the title, the fast non-equatorial X-ray winds in black hole X-ray binaries using disk refraction spectroscopy and also the absorption spectroscopy with the focus on this particular black hole transient, the MAXI J1820+070. And I just want to acknowledge these wonderful collaborators here. So let me just start with what we can learn with NuSTAR observations in the context of the black hole transient binary systems. And of course, the NuSTAR has been instrumental in constraining the refraction components in the hard X-ray, and also some of the ion K atomic features like the emission line from the Krishnan disk, and also the highly ionized absorbers. So I know that the audience, there are lots of experts in refraction spectroscopy in the audience. So let me just quickly review of these two spectroscopic methods. So from refraction, we can constrain the Compton refraction components as well as the soft excess components by incorporating some of the generativistic models to estimate the black hole spin and ion abundances. And among others, the refraction also allows us to say something about the inclination of the system and also the disk density. In parallel, the NuSTAR has been finding some of the interesting fast absorbers. And from the absorption spectroscopy, for example, you can constrain by using some phenomenological models such as Gaussians or some generic photoionization code like X-star or Crowdy to constrain the ionization state of these absorbers that you see here on the screen at about 7 or 8 keV, most likely attributed to hydrogen-like ion or maybe helium-like ion. And also the line of sight velocity from the blue shifted lines here, which also tells us something about the location of these absorbers and column density of these absorption features, with some of the a little bit more complicated absorption models, such as the one I'm going to show you in a moment. We can also say something about the inclination and the density of the base of these high velocity winds, which is launched from the surface of the accretion disk. So I just want to highlight that these two properties about the accretion disk in black hole X-ray binaries, namely inclination angle and disk density, they can be independently constrained by using two separate diagnostics, such as refraction spectroscopy and also the wind spectroscopy. So here is a gallery of a very small sample of black hole transients, just 4 objects here, because NuSTAR has been successful in constraining the refraction components, and the model in these, at least in these 4 objects, seems to favor a very low inclination angle, such as 40 degrees, 30 degrees, or definitely not the equatorial winds. From the absorption spectroscopy seen in NuSTAR data, we can also learn that these absorbers are quite high velocity, not quite the ultra fast outflows we see in AGN, but considering that these are black hole, stellar mass black hole binary systems, 4% or 6% of the speed of light is extremely fast. The quantum density from these absorption features seems to be also large, 10 to the 22 or maybe 10 to 23 atoms per square centimeters. And from photoionization models, these absorbers are also characterized by very high ionization parameters, such as log xi of 3 to 5. So with these, we try to account for both refraction components and these high velocity absorbers, which seems to be non-equatorial. And our interest is to simultaneously account for these two spectral components in within a single context. So again, I'm not going to go through the details of the refraction models, but in the end of the day, in our work, we decided to use the Reflinox-based high density refraction model, which was used by Tomsic et al. In 2018, based on the disk models by Ross and Fabian, 2007. So just the characterization of this high density accretion disk refraction component is that the continuum was explained by the non-thermal components Comptonization model, and the ion abundances and the high energy cutoff energy are both variable, so it is not fixed. Most importantly, this particular high density refraction model allows us to go up to 10 to the 22 atoms per cubic centimeters for disk density. Now, this is a really extreme domain in accretion disk density domain. So there is an uncertainty, and I think that people are really working hard to see if this high density disk really exists in nature. But at least this is one attempt. The atomic data is coming from the Chianti, and this is still in progress. So this is the refraction model, the high density refraction model that we are going to use for refraction. At the same time, since these seem to be non-equatorial accretion disk winds, we also propose to use the magnetohydrodynamic disk wind models, because as you can see in this simulation showing the streamlines of MHD driven accretion disk winds, the magnetic force, which is J cross B force, can naturally drive the winds, not necessarily in the equatorial high inclination direction, but also the paraboloidal direction towards the funnel region. And that's because of the magnetic field geometry. And so we use this MHD disk wind models by numerically solving the ideal MHD equations, which is coupled to the Grad-Shafronov equation. The bottom line of this model is that the overall density structure of this MHD disk wind can be conveniently expressed by this radial dependence in this self-similar format, with some angular dependence of the density, which is calculated numerically. And this N19, this is the density normalization of the wind. So we can constrain this N19 right at the launching radius, at the innermost disk radius of this wind. And that density provides us some sort of good proxy for accretion disk wind density as well. Okay. So we use this particular disk wind model, and then we couple this wind solution to extra photonization code to calculate the column distribution of the elements. So here comes the amazing NuSTAR data for MAXI J1820+070. So we use multi-epoch NuSTAR and NICER observations back in 2019. We're going to see, explain the 5 different epochs, as you can see in this hardness intensity diagram from MAXI light curve. On the right-hand side, you see the absorption components from NuSTAR data across different epochs from E1 to E5. So again, we decided to use our MHD wind framework for absorption features, which is coupled to the high density accretion disk refraction components. And so since I don't have much time to go through all the details, this table is basically, this is the punchline of my talk. It's still preliminary, but I can share with you that the red column, MHD wind, tells us the wind normalization at the launching radius on the disk surface in log, and the blue columns are the values constrained from this high density accretion disk refraction model. So you can see that there is a pretty good agreement in disk density. And of course, these are very high density on the order of 10 to the 21, or sometimes it's close to 10 to the 22 atoms per cubic centimeters. And also the inclination angle from these 2 diagnostics, one from refraction, one from the absorption spectroscopy, they also suggest a relatively low inclination at the statistically significance level. And then these are the best fit spectra in blue that you see in this animation. So we are kind of encouraged by these preliminary results. And what we are thinking is that, okay, so these are very, very high density accretion disk. But whenever we see non-equatorial ultra-fast outflows like these absorption features with massive quantum density, maybe this is a necessary condition for the system to produce high velocity non-equatorial winds, because these quantum density in the absorption features must be originating from somewhere, which is most likely accretion disk. But if these are really low inclination, then the density of the wind, it's probably hard to see in this diagram, in this picture, but as you go towards the polar region, density quickly drops. So it's almost a vacuum, very tenuous wind on the funnel region here. And then inside here, near the symmetry axis, the wind is not present. Instead, we may have jets or something instead. But the point is that for low inclination, the density of the wind is really low. So for us to be able to see the high quantum density at this low inclination, the accretion disk has to really have a high density to begin with. So that's our interpretation as to why these 4 systems have high density disk. So this is the take-home message. So I told you that we use both refraction spectroscopy and wind spectroscopy independently to make this diagnostics of disk density and inclination. Non-equatorial fast winds of massive quantum density, they may require high density disk. Otherwise, we may not detect these non-equatorial fast winds. And because of the generic topology of the magnetically driven wind, these non-equatorial fast winds can also be naturally explained by MHD process, J cross B force. For the outlook, I want to, we want to see how ubiquitous this is, or how rare these non-equatorial disk winds. And we also want to pursue if there is any soft X-ray counterparts in low ionization regime, maybe microcalorimeter observations with the Krishnan and Athena might help to provide more clues. Either way, this is still ongoing, but we would like to see if these non-equatorial fast winds are accompanied by high density accretion disk wind. So again, I want to thank NuSTAR and all the teams for providing this exciting science. And I think with that, I will stop. Thanks.
Yeah, there should be a mic there.
So it's very interesting results with these densities. And I just wanted to notice that there is a simple test of this density from these high density models. Namely, you fit both this density and ionization parameter, as well as you have an estimate of the incident luminosity, knowing the distance and bolometric flux in X-rays, and then from those numbers you get the distance between the corona and the disk. And at least in two objects I'm aware of, in similar states, in GH3-4 and Cygnus X-1, the two numbers disagree by 4 orders of magnitude. And I think it will be very interesting to see how it works for your case.
Okay, thanks so much for your comments. Yeah,
this is a paper in 2020 that we wrote on that.
Okay, 2020, and
yeah. Me with Barbara DeMarco.
Okay, thank you. Thanks. Yeah, so that's a very interesting comment, and we actually are able to calculate the ionization parameter from our wind models, and also from, of course, from the refraction components, and they are systematically high end in log of Xi. Like I said, the 3 to 5, and these are the fast absorbers here are systematically closer to the black hole. Definitely within the order of a few hundred gravitational radii. But yes, it's a very interesting suggestion to make connections to corona and other properties. Thank you.
Okay, so let's thank the speaker, and next speaker, Andre. Yeah, right here. Yes, yeah, right here.
So can you put on my?
Yeah, you go ahead.
Yeah, no, but I need my view graphs.
Well, you have to put them on, right? Tail. Yeah. Have you made arrangements?
No, I sent email to Matteo with my presentation. Sorry. Oh.
Okay. Matteo here.
I asked you if it's okay to send by email the PDF file.
I see. Okay. Well, they probably have it here. One moment. They're going to.
Okay, maybe you can. Sorry for the delay. I'm sorry. I should have double checked it.
Well, why don't we switch you with the following one?
Sure. Yeah.
Okay, let's
yeah. That would be. This is what I want.
Katrina. Is Katrina here?
Oh. Douglas
Sokolova-Lapa. She's not here? He's not here? Okay. About Riley Connors. Just because we want to keep this going here. Come on up. You win the prize. You have everything you need?
I just gave him the slides. So.
Oh, they'll load it. Let them know to load up yours.
Oh yeah.
We'll get through this. Don't worry. Okay, you're on.
Okay, good. You have to forgive me if it seems like I'm laboring through this talk because I'm extremely tired. I just came from a wedding in Poland. I woke up at 2:30 this morning in order to get here on time. But nonetheless, that's how it is. I'm going to talk about this source. Okay. Yeah, ahead and back. Sweet. Okay. I'm going to talk about this source for you, 1543-47. This is a black hole X-ray binary. It went into outburst last year in June. It was extremely bright. It went beyond, I think, beyond 9 crab. At its peak, was very quickly caught in transitioning into a soft state within, I think, within a day or a couple of days. And then since then, it's been decaying through its soft state for a number of months, 6, 7, 8 months. And then it kicked into a low hard state after that. I'm going to talk about all the soft state observations of this source with NICER and NuSTAR. We triggered a NICER geo program to observe it 4 times, 4 NuSTAR exposures of 20 kiloseconds simultaneous with 2 kiloseconds of NICER. But NICER was monitoring this source ever since it started its outburst, basically. So there's a lot of data. And as I said, it's extremely bright, so it's good signal to noise data. And just before I get into that, just as a way of an introduction, because not everybody here works on X-ray binaries, the reason why I find, well, the thing I find most interesting about this area of research in the past 5 or so years is this connection now we have with LIGO observations. So these are gravitational wave observations of merging black holes, which is another way for us to study possibly a different population of black holes, but nonetheless a lot more black holes. And one thing that's coming out of that is that we see the spin distributions differ between 2 classes of objects. So the black hole X-ray binaries that I'm studying, we typically find relatively high spins. There's some disagreements, but we tend to find quite high spins in some of these sources, whereas in the gravitational wave sources, the spins are much more low. And it's a puzzle that probably has an easy solution. These are just different calculations, but we're not really sure about that. So I think when it comes to studying black hole X-ray binaries, the biggest problem we have is that there's a lot of degeneracy in all our models. We don't understand exactly what the accretion flow is how it's structured during different states, and we need to know that information in order to measure spins. So we have a little bit of a in terms of models. Anyway, this is the sort of general phenomenology. I can't say that word at all. This is the characteristics of X-ray binaries. They go through hard state, across to the soft state, and then decay back down again with some different classifications of states in between. And there's a lot of things we don't know about how the source is behaving in all these different states, even now, even though we've been studying these objects for decades. And we have observations all across the electromagnetic spectrum. We don't know, for example, at what point during the hard state has the disk filled right in towards the black hole to its innermost stable circular orbit. So we don't know the structure of the flow in the hard state. So that's an unknown that makes it very difficult for us to robustly measure spins and many other things as well. There's a rich phenomenology as the sources go across to their soft states. We see a lot of changes. The jet evolves, eventually goes away. We see a transient outflow and then it disappears completely. We have quasi-periodic oscillations that are evolving in frequency as you go across to the soft state. And then in the soft state in more recent years, so here you're essentially just dominated by the thermal disk component. but we're starting to see signs, at least, that we're picking up some other types of emission that hadn't been seen before, that had been predicted but not observed. For example, returning radiation. So this is just radiation that comes from the disk itself and is reflected back off the disk. And the plunge region emission. So this is emission from gas from plasma that's falling inside its ISCO, inside the ISCO of the system. So there's a lot of things there to try and explain, and a lot of things that we don't understand very, very well, which makes it hard to measure things like spin. And that's why, for example, you get all these different measurements of spin for even one source, and often with the same data. So for U1543, this was first discovered in 1971 by Uhuru, and it has since then gone into four additional outbursts. It went into outbursts roughly every 10 years until 2002, when it then had a roughly 20-year period of quiescence until it went into outbursts last year. And it may not be a coincidence that this seems to be an extremely bright outburst, so perhaps it's had a lot of time to build up mass in the accretion flow. The counterpart was picked up in 1983 by Pedersen, and it's a relatively high mass. When I say high mass, I mean it's something like 2.7 solar masses, and it's an early type star. And studies of the orbital characteristics have allowed us to get, for example, the mass of the black hole initially known to be a compact object, but now it's known to be a black hole because it's got a relatively high mass. Inclination, the limits I have on the slide there are very broad limits. Arguably, the inclination is known to more precision, sort of like 20 degrees or so. And yeah, as I said, the companion mass, 2.7, it's about 7.5 kiloparsecs away, and it has a roughly one-day orbit, a little bit more. And this is data from, this is RXT data from the 2002 outburst. The spectrum in that outburst and in all outbursts actually is very disk dominated, very early on. It's a very soft source. The disk gets to above 1 kV or so, and it has a relatively soft power law component above gamma of 2. And the disk component is consistent with an accretion flow that's within 5G or so, 5 RG or so, which would be, it would be close to the ISCO for a relatively low to moderate spinning black hole. So these are some of the spin measurements. I'm not sure if I picked up every single one for the slide, but these are a number that have been performed over the years by modeling that PCA data, either from the point of view of modeling the continuum, the thermal continuum. So this is, you're just modeling that thermal disk component that has distortions due to relativistic corrections, because the disk is very close to the black hole. It relies on, you're assuming that the disk is at the ISCO when you do this kind of measurement. So there are some systematics there, but that's one method. And the other is, of course, reflection modeling. So looking at the fluorescent iron line and seeing the broadening. If it's a broader line, it's a higher spin black hole. And you can see that there are very different measurements from exactly the same data with different methods. And I think that's both, you know, there's a contrast between those two methods, but then there's also changes to the models that are used in either case. And that can have an impact on spin measurements. Also, just how you go about fitting your data can change this constraint. But nonetheless, it seems not to be a really high spin black hole. It's sort of moderate, low to moderate spin. Right, so let's get on to the actual outburst from last year. So this is the NICER data in blue and the NuSTAR data in red. I said in the beginning that we triggered a GEO program that was 4 observations. There were, we had 6 subsequent DDTs approved to continue observing the source with NuSTAR because we were seeing some slight changes in the power law component. So we wanted to keep looking at it in the hard band. But as you can see, it was monitored with NICER for quite a long period of time. There's actually more data than I'm showing on the slide here, but this is just all the data that I'm working on. So it got extremely bright at peak. Like I said, it was about 9 crab or so. And NICER actually had to have most of the detectors turned off. I think they had 7 detectors on out of the 52 because it was so bright. So due to telemetry saturation. So what I tried to do to begin with is to just take a look at all the NICER data, see how the disk component is evolving over time, because we have really high quality data. We can take very small snapshots. So this is data taken from maybe, it varies sort of tens to hundreds of seconds of exposure with NICER. And what I see here is, this might be a little bit difficult to parse on the slide, but you see all the data in blue. That's the luminosity of the disk as a function of disk temperature. And you see three lines, three curves. The green curve is just Stefan Boltzmann law, right? So temperature to the power of 4. But that's if you're measuring the effective temperature of the accretion disk, which we're not really measuring. We're measuring what we can see, which is the color temperature. And that can be distorted. You usually get some spectral hardening as the photons are traveling out of the disk atmosphere. So you may actually expect, you should actually expect, the theoretical predictions suggest that you'll have this yellow line or gold line, which is more like T to the power of 3. So which way around is that? So for a given disk luminosity, you actually see a hotter disk, let's say that. And I'm seeing the opposite in this data. And I think I haven't explored this very much, so any suggestions from the audience would be good. But it looks like it's a steeper trend. It's sort of 4.7 or so. And I think that may be due to a change in the structure of the accretion flow as it's getting to high luminosities. But then again, if you plot the disk normalization as a function of temperature, it's quite stable, which suggests that at least the accretion disk is not moving very much. The inner edge of the disk is staying where it is. I can see some evidence of a slight trend maybe beyond 1.1 kV. You can see the blue points start to rise a little bit, but they're all within the 5% level. So the source to within 5% is pretty much staying where it is. Yeah, so that's all I'll say on that. So I wanted to just show one of these simultaneous NICER+NuSTAR observations. I'll start by looking at the NuSTAR data. So this is from, this is very close to the peak of the outburst. It's extremely high signal to noise data. It's on the order of thousands, particularly around the ion line because the source is very soft. It's obviously very bright in the soft band. So this is what that data look like when you fit it with, of course, I'm only showing 4 to 8 kV here because I want to focus in on the line. Of course, the data is broader than this, but I fit the whole continuum with a Comptonized disk model and then look at the residuals. And I don't want to make any strong claims at all, but when you look at it, you see sort of a double peaked ion emission line. I can't claim that it's significant and it may be consistent with just being one peak. But if you just throw a Gaussian model at it and a smedge model, which is a smeared edge component beyond 7 kV, it's not an accurate description of the reflection component, but it's an approximation. It's very difficult to fit that data with one broad Gaussian. Instead, if you throw 2 at it, you get a very good fit and you model out all those residuals. This is something that I see very prominently in this first observation, but not really in the rest. And I don't know if that's a signal to noise thing. We're a bit stumped on it actually. But so let's just show the simultaneous data. So this is that same data set with NICER as well. As you typically find with really bright sources, they don't always play well together, these two instruments, like most. So I'm finding it a little bit difficult to model them simultaneously. They don't agree very well in the band in which they cross over. But I sort of see some structure in the ion emission line in the NICER data, as well as the NuSTAR data. I don't think it's one-to-one. It doesn't look exactly the same, but you see some structure there. So that's somewhat encouraging, at least. We have a couple of ideas, or a few ideas, as to what that double-peaked line could be, what could explain the complexity that we're seeing there. Could just be that, to start off with, it could be that the reflection models we use are relatively simple from a geometrical point of view. It's just a slab of material, a slab, no structure there, nothing complex. And if you add more complexity to the geometry of the system, you may expect to see slightly different features there that we're not capturing. So it could be that it's difficult to model these data with the models we have, and that's just the way it is. And there's no special thing going on. Or it could be something like returning radiation, which we do often see, or we have seen in a few sources now, when the source is very bright in its soft state, has a very hot disk. It can be that if you make a prediction of how much of that radiation will return to the accretion flow and be reflected, it can outweigh the reflected power law component. So this could be a sign of that, and we don't have yet a great model for that. We've got a model that's kind of, in a way, it's like piecing a couple things together, but it's not fully physical. So we're not self-consistently calculating the returning radiation. So we're looking to develop a model that actually does include that more consistently. So if you go and check out Thomas Dowser et al. Paper just got accepted, I think, in recent weeks. He's developed a model for returning radiation that focuses in on the second order reflection component. So this is reflected emission that then returns again to the disk. And this will slightly change the observed reflection signatures. So we'd like to do this with the thermal emission as well. It could also be that we're seeing some emission from within the plunge region. It could be reflection from within the plunge region, something like this. So inside the ISCO, and that's something, again, that's not captured by our models. So, but these are just wild guesses essentially at the moment. So we haven't developed any models to actually do this. So it's something we need to test, and that will be a subject of future work. So just to summarize, how am I doing for time, by the way? Good. So it's an extremely bright source. It was, I think, the brightest outburst it's had last year. With very good signal to noise data here. The disk luminosity against temperature doesn't seem to follow the expected scaling law. And I theorized that it could be a change in the accretion flow because we're at very high luminosities. So a sort of slim disk as opposed to a thin disk. And yeah, the first NuSTAR observation reveals a pretty complex ion emission line that we cannot yet explain. So we're going to start developing a model that can try and treat that and see what we get from that. So that's it.
Thank you.
More questions?
Here we go.
Awesome. Can you bring up the LT to the not 4 slide again?
Yeah.
I feel like I might have spotted your issue here, which is that you're plotting luminosity in quite a limited band. As you change the temperature of your, like it's the bolometric flux, you should go as LT to the 4 of the disk, right? But as you're changing the temperature, you change the fraction of your bolometric flux in your narrow observed band. And I think that will push you above LT to the 4 in this case, because a slim disk should go as LT to the less than 4. So I don't think that's really consistent with a slim disk either.
Right.
And the fact that your normalization is constant probably is suggestive that in a bolometric sense, this is tracking LT to the 4. So you might just try that, making it a much broader band.
Wider, yeah. Okay.
Yeah, and that might correct your issue. More of a comment than a question, I guess. Will you do that?
I'll do that.
Thanks.
Any other questions?
Just a curiosity, really. It looks like you're well above 1,000 counts per second in NuSTAR.
Sorry, repeat it. I couldn't hear you properly.
Take this off. You said this is a really bright source in this brightest NuSTAR observation. It looks like you're well over 1,000 counts per second.
Yeah,
in
3,000 or
NuSTAR.
4,000 in the, yeah.
Just out of curiosity, how much is dead time then? How much of that observation are you actually getting to work with? Is it like
It's a few,
just a few
it's
percent?
1 or 2 kiloseconds of data, yeah. Out of a 20 kilosecond exposure.
Okay, so yeah, you're really losing most of it. All right, cool. Yeah, just curious about that. Thanks.
One last question.
I guess, so my question is that you said that we don't know whether the accretion disk continues all the way down in like the hard state, but I was under the impression it was generally thought that it's like truncated and you have like a advection dominated accretion flow or something like that in there. Are you saying that there's now evidence that that's not the case?
I'm saying that there's conflicting evidence and has been for a long time, I would say.
Well, then I don't know anything.
So, okay, for example, it's not a question of whether there's any truncation at any point. There certainly is when these sources are at low luminosity. I don't think that's under any, like there's an agreement there. But it's as the source gets brighter during the hard state, at precisely which luminosity the disk has filled in, we're not really sure. There's disagreement on that.
Okay.
And that's, I don't want to get into all the details, but one issue here is in modeling the reflection spectrum.
Okay.
You can't get an extremely broad line very easily if you have a truncated disk. So it's just explaining that, and yeah, there are disagreements about it, but
Okay.
Let's thank the speaker. I think we should go back to the regular session because we have somebody remote. So Douglas Buisson.
Hello.
Okay.
Can you hear me?
Douglas, are you there?
Yes. Can you hear me?
Yeah, go
Okay.
ahead. We don't see your slides. There we go. Okay.
Yeah. Okay. Yeah.
Very good.
Thank you. So yeah, unfortunately, this time conflicts with the farmer outside my house has decided to mow a meadow. So hopefully his tractor is not too loud, but I'll try to get on anyway. So yeah, I'm here to give one of several talks about MAXI J1820. There's at least one more, and possibly some posters as well. So let's start with a brief introduction to the source. I guess many of you will have heard of it, not necessarily everyone. So it is a black hole X-ray binary. It's had sort of one outburst that we've detected. So it was discovered initially in 2018 with this really monster outburst that's shown on the right here. And it basically has all the good properties that you could want of an X-ray binary. So it's fairly nearby, which makes it bright. It also has very little absorption, so you can measure things nicely right down into the soft X-rays. And also it had a nice long outburst, giving you plenty of time to point telescopes at it and see what's going on. And therefore there are many observations. So on the right, you've got a hard and a soft band. The hard band is BAT. You can see, even though BAT is significantly less sensitive than NuSTAR, we've got really, really tiny errors for most of this. This is because it was one of the brightest things in the sky at the time. And then NICER monitor it basically every day. And NuSTAR did plenty of observations. Those are all the vertical lines at the times of the NuSTAR observations. So it did other interesting things. The canonical picture of a Q, it played around in the hard state a little more than you see in your basic pictures. Quite a few sources do this, but this is just really useful because if your data just all go in one direction, all your parameters will all go in up or down, and you can't really tell which parameter is driving what. But when a few things change in different directions, hopefully some of your parameters keep moving, others don't, and that lets you separate things out and work out what's going on. So I'm mostly going to be talking about the hard state, and given the topic of the conference, mostly with NuSTAR. So in the HID, these are these grey triangles over here, which are going to become nice and colourful soon. So let's look first at the spectra. So these are all the hard state spectra, plotted as a ratio to a power law. The power law changes in normalization bit, in hardness a bit, but you can see that the relative reflection stays fairly constant. You can see changes at the high energy due to changes in the coronal temperature, which this was just a plain power law, so that's not included. And this iron line, which we've had bits from Aaron and Riley on how this is useful about looking at the geometry of the inner disk, particularly in the red wing, really stays very constant. So you can see it changes a bit in the narrowest parts, which tells you about the illumination of the bits in the disk further out, the velocities are lower. But the red wing is what really tells you about the innermost radio, which is going to suggest that the inner radius doesn't change that much. And that agrees with some nice results that Aaron had with NICER reverberation. So that's quite a different method to give similar results, which is nice. We can also look at the timing properties. of the same observations. So you have the same colors. These have been vertically offset for clarity, but you can still see there is a big change in where these spikes occur in frequency. These spikes are called quasi-periodic oscillations, and they're generally considered quite useful as specific frequencies. If you have a model for how they map into the other physics of your system, it should be able to give you characteristic sizes. And lots of models exist and are quite popular for how the QPO can be produced at the inner radius of the disk. So we can measure these QPOs quite nicely. We've done reflection fitting, which gives us the inner disk radii, and we can just compare them with each other. And what we get is the inner disk radius really stays quite constant at the colorful points. But we have various models here, all of which predict much larger changes in inner radius to see the observed changes in QPO frequency. So if we have one of these QPO models, most of which are precession induced, there are some other lines on here as well. But the characteristic radius that's governing the QPO cannot be the same inner radius that this reflection is measuring. Now, one option which I discussed when I published these results in 2019 was just a sonic oscillation across the corona. That gives you about the correct magnitude in QPO frequency change. Everything is out by about a factor of 30, but these are fairly complex systems. You can imagine that the overall coronal size has some twisting in it, and therefore a sonic oscillation actually propagates further in the same apparent size. But there was something else which didn't necessarily quite fit with everything else that's going on in the source. I'll discuss another model I've been looking at, which comes up with an alternative explanation for all this. And that's looking at the inclination that this all implied. I don't have a plot on here because I'm basically comparing two numbers. You don't really need a plot to do that. So there are X-ray dips seen early on in the light curve, which frequently, but not always, happen in high inclination sources. They're viewed as sort of the top of the disk getting in your line of sight. But that's not a particularly certain method. You can have dips from other reasons, but there was also a nice radio observation of the jet, and comparing the two sides of the jet also gives you an inclination, and that gave quite a high inclination, order 60 degrees, plus or minus a few depending on which modeling approach you take. But all this reflection modeling gave a significantly lower inclination, again statistically plus minus a few degrees, but around 25 degrees lower in apparent fit. So you have two inclinations. You could say they both really exist in the disk, and there's actually a warp between them. So there are a few pieces of evidence that suggest that might be the case. If you look at the reflection actually at and after the state transition, the reflection modeling then starts to give you a much higher inclination that actually fits with the sort of the jet inclination. There's also some work by Andre, which I think he's going to tell you about a bit later, in which you fit the hard state with a forced high inclination, and that gives you a much more truncated disk. So that's another way to get rid of the blue shifted part of the line that you should see for a high inclination. Another suggestion is that there is some warping going on in the system. If you measure the optical polarization angle in the outburst relative to what you see in quiescence, that's rather different. So it's not really tied down what's causing the polarization, how the polarization agrees with either the spin axis or some other axis during quiescence, but it definitely changes. So there's some sort of warping in the system going on. Also, maybe the weakest suggestion is that the soft state really can't be explained with a simple disk. it needs a sort of double thermal model. But if you have two sections of your disk, that could be what's producing the two thermal components. So let's look at what disks would look like. So the most likely reason is that you have two angular momentum directions. The material starts having roughly the orbital momentum, the angular momentum direction of the orbital plane, or perpendicular thereto, depending on how you view your angular momentum. And then it needs to get down to the black hole spin axis once it's actually inside the black hole. And usually you need to accrete order the black hole's initial mass to significantly change its inclination. So you won't usually have accreted enough material to change it, and therefore these will be different in general. And at some point, the material is going to have to change its angular momentum direction. There's going to be some talk that's doing that, but a priori, we don't necessarily know whether this is at all measurable. So there's three very indicative diagrams on the right. So it starts on the right at the inclination of the orbital plane and gets to the inclination of the black hole at the end. But you could suggest that it happens very slowly and smoothly. It could be essentially constant and then change rapidly, and then get to the inclination of the black hole quickly. Or this middle section could really produce a bit of a mess. And also where this R warp happens, you don't initially know whether that's inside the event horizon, far too large to measure with X-ray reflection, or somewhere in between. But fortunately, people have done this theory, starting with the rather famous work of Bardi and Peterson, looking at how the lens flaring, which is one of the general relativistic processions, changes the inclination of matter. So as material drifts in, it both changes its position angle and so it moves inwards as it processes round and changes effectively the position angle of the orbit. So the initial analytic models said that this transition was somewhere around 100 to 10,000 gravitational radii, which might be a little hard to measure, but fortunately, when this has actually been done numerically, you do get a somewhat smaller radius. And also these fast oscillations that you see as you get close to the black hole in the analytic model start to go away as you get the velocity dispersion of the matter taken into account. So let's show a nice pretty picture of a numerical simulation. You have a much smaller transition radius. This is in gravitational radii. So here you have somewhere around 15 for these parameters. And also critically, the jet, you can see the effective edges. It's this pink line aligned with the outer disk plane. This is still a very, it's still a relatively small part of the disk, but it's the part that doesn't align with the black hole spin axis. You can see that quite clearly. So let's just try fitting this to the NuSTAR data. We don't really have a full model for this rather complex geometry yet, so we can take the simple approximation of adding two flat disks at different inclinations. There are a few different ways in which things haven't fully been taken into account, but none of these affect the fact that you always see the reason of maximum blue shift, which is the most important thing in determining the disk inclination. So that's what we've done. We fit that to each of the NuSTAR spectra we had before, and it gives a similar to slightly better fit. So you can see the outer high inclination part has a peak at a slightly higher blue shift in the model plots here, and you get a transition at order 10 RG, which is quite useful. So what happens if we look at that radius and compare that with the QPO frequencies? Well, we can do that. It's a little bit noisy, but we do start to see it aligning roughly with the lens-Thirring precession. There are a few parameters, so this just shows changing the spin. Each of these is the lens-Thirring at the warp radius for a single particle. So if you treat the whole inner flow as fixed together as a economical hot flow, you get something that's rather too flat. But if you treat the outer radius as dominant, then it aligns fairly well. But of course, for this to work, you really need to link the precession to actually induce some flux changes. There are a few possibilities. I haven't really got a fully convincingly thought through model. So as this inner disk precesses a little bit, governed by this lens-Thirring effect, if the corona just follows it and it's somewhat anisotropic, as its angle changes, you'll see a slightly different amplitude of the flux. Whether that produces enough amplitude is not clear. Or just you've got this break radius and you have a load of fluid dynamics. So you could just get a resonant effect that all your general broadband mass accretion rate variations produce a sort of resonance that bounces across and starts to build up at that frequency. But I haven't settled that yet, so I'll just leave you with the conclusions so far, which is that we really expect to be seeing warps in X-ray binary disks in some places, and the reflection data is starting to get good enough to constrain them. And it's one option for MAXI J1820. Okay, thank you. I'll take questions now.
Thank you. Any questions? Go ahead.
Yeah, a very interesting possibility. There was a paper by Thomas et al. 2022 in which they found evidence for warping in this source, but at much larger distances from optical data. So what is the relationship between U warp and they warp?
Yeah, this is potentially a different mechanism.
Yeah.
So yeah, one thing I didn't mention as we were going through is that the sort of the radiative warping that's produced by an instability is a very different mechanism, and that does occur at much larger radii. So I think I don't remember off the top of my head how large the amplitude of their warps were, but I think they could well just be separate mechanisms acting at different radii. There's probably some link between them. You would expect there to be. But you see the onset of their super hump does happen at the same time as the changes in QPO frequency switch round. So it's possible that these optical warps are propagating across the disk, and when they get to the edge, they are sort of bumping up against these edges of the disk with enough effect to have a noticeable change.
Are there any more questions? Let's thank the speaker.
Thank you.
Wow. This is a pointer. Okay?
So, no, sorry, but what about my?
Yeah, they're coming up. Yeah.
Okay. Okay, perfect. Okay, so sorry for this delay. Yes, I know. I'll try to talk also about this exciting source. And a few questions I would address is the geometry of the accretion flow, which was already discussed in the previous talk, and then also about electron-positron pair production and the jet in that source. And the source already was reviewed in the previous talk. It is a very exciting source, with a lot of observations, including NuSTAR, and very well measured parameters. The black hole mass is 6 to 8 solar masses. And actually, in my group, we have done quite a number of papers, which I just wanted to list here as an advertisement, but I will review only some of them here. And as already mentioned, there is this evolution of disk from quiescence to the soft state. And we know for sure that this is almost for sure that this is truncated in the quiescence, and this follows both from theory. In order to apply the disk instability model to black hole transients, you need this to be truncated at about 10 to the 4 gravitational radii, and then the inner part of that flow is a hot gas. And on the other, and this was actually confirmed relatively recently by Bernardini et al., who found that the width of the H alpha line during the quiescence is actually indicates quite large truncation radius. On the other hand, we know that at ISCO, at the soft state, the disk is at ISCO, and the quiescence geometry is here, that there is just an outer disk, then hot flow and also a jet, and this is very similar to at least a part of the hard state. But then there is this discrepancy, this controversy already mentioned. This is a view graph from Javier Garcia, that there are basically two schools. Now, one model, one group of people fit the truncation radius in the hard state as a function of luminosity in Eddington units to be of order of 100 and more. On the other hand, other measurements show it to be very close to unity, to ISCO. And one model that is very popular for this calculations is Lampos. And actually, original Lampos was invoked simply due to mathematical simplicity. If you want to calculate reflection, it's simplest to put your source on the symmetry axis. But then it was taken as a real geometry, and there are a number of problems with that. First, this Lampos needs to intercept enough seed photons for quantization, and if it's small, it's very tough, as pointed out by Dovchak and Don. And then there were a lot of results in which the Lampos was very close to horizon, which makes a lot of problems with relativistic corrections. If in the source frame, most of the photons go to the black hole, and then there is a runaway pair production. But in our paper in 2021, we compared two ways of modeling with Lampos. As already mentioned in the previous talk, the results of Buisson for that particular state, I will mention, it was that the disk is close to ISCO, and then inclination is about 30 degrees, and iron abundance is 4 to 7. And then, as already mentioned in the previous talk, there is this discrepancy of this inclination with observations. And then if the donor is known to be a low mass subgiant, and it's unlikely to have such high iron abundance. And what we found in that paper, actually, after a long discussion with Douglas, that there are two solutions in the truncation radius. We can have one solution at ISCO, more or less, which has inclination of 30 degrees, and another one with large truncation radius with inclination of 60 to 70. And this inclination actually comes from the fits. It's not in any way adjusted to other data, and iron abundance of unity. And also, as we found a posteriori after doing all these fits, we found that we can use integral data, which, well, doesn't work. Integral data are shown here on the right bottom, and they were more or less simultaneous with NuSTAR, and we fitted them without any prior knowledge of them, and we found that our solution, which is in blue, the spectrum agrees very well with integral, while the solution in which the disk is at ISCO disagrees. And this also was later confirmed in a paper by DeMarco et al. That characteristic frequencies during the time lags during the hard state as it transits to the soft state indicate truncation of the disk. And furthermore, these Lampos models are very simple, but the overall behavior of the source is very complex. And as found in a number of papers by Mahmoud et al. And Kawamura et al., both with Krishnan, that they found that we need at least two hot quantization zones or even more, and they were able to fit full data sets with such a model. And we then included into NuSTAR data integral data, finding before that they were some of them were simultaneous. And what we found is that the two data sets agree very well in the region of overlap as shown here. This is NuSTAR and integral, but then actually integral data completely disagree with thermal quantization models. They require a hybrid high energy tail, and this tail was measured actually up to 2 MeV. And this hybrid quantization models correspond to distribution of electrons with Maxwellian plus a high energy power law tail. And we were able to get very good fits with inclination of 65 degrees and truncation radius above 20 gravitational radii. And our kind of toy model geometry shown here, we have a soft quantization which is a corona above a disk, and the reason it's soft is because it's cooled by the seed photons from the underlying disk. And then we have a large K-height hard quantization component in the inner part, and it reflects from remote parts of the disk. And altogether, this model gives perfect fits to all the data sets that we tried. And one interesting question is, what about Pearl production? If these photons go up to 2 MeV as observed, whether we see any signature of Pearl production. And what we found is that basically there is no trace of any broad annihilation line. The 2 sigma per limits are shown here. The best fit is at 0. And we also calculated per equilibrium models for that situation, and it found it's completely consistent. The per equilibrium fraction is much less than unity within the flow, which is of relatively large optical depth. And this again also brings about the question of the abundance of leptons of matter in jets, whether jets have a lot of ions and electrons, or are dominated by electron-positron pairs. At least in blazars, there is evidence that there are a lot of pairs which dominate by number. And what we calculated in another paper with Alex Titarenko and Marek Sikora is Pearl production in the base of the jet. The base of the jet, if the jet is magnetic, this base is devoid of matter because the gyro radius is many orders of magnitude lower from the gravitational radius, and matter is not able to penetrate to the jet. This is simulation by Czechowski et al. And then you see that this is high density matter medium in this part, but then the jet is basically very low density. However, photons from the accretion disk can collide within that region and can produce electron-positron pairs. And from the model, from using NuSTAR integral data, we're able to calculate the rate of pair production, which is about 10 to 40, 10 to 41 per second. And then from the synchrotron spectrum and timing of the synchrotron jet, we also could calculate the rate of electron and positron flow at high region of some millions of gravitational radii. And we found that these two numbers amazingly agree very well. So these two numbers are based on completely different physics and completely different data. So it's quite amazing they agree. And we, in the meantime, wrote another, we did some work for TC120 radio galaxy and found that we find the same results. So this indicates that accretion flow plays a big role in formation of the jet in providing leptons for the flow. Otherwise, it's actually pretty difficult to get those leptons. I mean, the magnetic jets are by nature purely magnetic. And then the process involved in original papers, the pair production in ergosphere, we found is efficient only very low luminosity sources, and in high Eddington ratio sources like MAXI, it's inefficient. So our conclusions are here. We found a lot of evidence for this truncation, and I think our spectral models are quite realistic and are based on broadband data. In the meantime, we also included HXMT data and also found this truncation. And then the hot accretion flow consists of at least two or even more components with different temperatures and different reflection properties. And the distribution of electrons at least in the hard component, the soft component is difficult to constrain because it contributes very little to high energies. The electron distribution is hybrid with a parallel tail, and then pairs are produced by the equilibrium pair density in the flow is low, and we see no annihilation line. And on the other hand, pairs can be produced above the hot flow in the jet base and can provide enough leptons to power the jet as measured by the synchrotron emission in the radio and infrared region. So thank you.
Are there any questions for the speaker?
So you say that like the lamppost geometry is physically inconsistent near the event horizon, but you don't really specify how close to the event horizon you're talking about.
Well, there were papers in which the height above horizon was 0.1 RG.
Oh, okay.
I mean, many papers like that. But in that particular case, it was not so close. But I just, as a general comment on in the paper by Buisson, it was not as close. But in many other papers, the lamppost was placed very close.
Okay. Also, like, why is it physically inconsistent exactly?
Why?
Yeah.
Well, I think the one point is certainly the underlying continuum. The underlying continuum in models in which people claim broad lines is just taken as a power law. If we have more than one quantization region, we have more or less a soft excess below the line energy. So this soft excess in the continuum is then fitted as a red tail of the line. And also there is this curious double solution, even in the Lampos model, which I showed on this view graph, that we have degeneracy in the data. And then also I would like to comment that the models in which the disk is at ischor and constant, but then the corona height changes, also would imply quite dramatic changes in the line width, because if you put your lamppost at, say, 20, 30 Rg, it would illuminate most regions of the disk also at 20, 30 Rg. If you put it close to ischor, it would illuminate innermost part of the disk, and therefore it's clearly that such fits would also predict strong changes. And as far as I'm aware, such fits have not been tried. In the paper by Erin Kara, they just mentioned that as a possibility, but there were no specific fits of that model.
Okay, let's one more quick question and a quick answer.
Yes, hi, Andre. Very nice talk. Thank you. And can you speculate on what would be the mechanism by which the bursts are produced in jets? This might be beyond the scope of your presentation, but do you have any speculation?
No, I think bursts can be produced by the mechanism I mentioned, that if you have accretion flow that emits up to half MeV and more, and we checked two sources so far, MAXI J1820 and 3C120, and in both cases there is agreement. The problem is to get enough soft gamma ray data for those sources. And also there was a paper by Marek Sikora with you, in which you just take some fixed percentage of energy, put it above half MeV, and then you also find good agreement.
Okay, so it's just a per production by
Sure.
photon,
Yeah.
right?
Well, I
Okay.
mean, one possibility. There are this.
Let's
Okay, sure.
very good. But just to keep things going, we
Of
all
course.
want to get to the coffee break. We have one last speaker. Very good.
Hi, I'm Ekaterina Sokolova-Lapa, and I'm really grateful for the organizers for the opportunity to present this work today. And I will use this opportunity to finish this part of the session before the coffee break, unexpectedly talking about the neutron star binaries again, moving away from the black hole binaries. I will tell you about the BH X-ray binaries. GX304-1 is one of them. And our attempt to model the system at the low luminosity state in quiescence, using the polcap model, which I will describe in a bit. And I will tell you first some basic things about the BH X-ray binary systems. Give some information about the accretion at high and low mass accretion rates. These are pretty different regimes. Then tell you more about our attempt to model the low luminosity accretion, low mass accretion rates, and the application of this modeling to the system GX304-1. And finally, I will tell you what we can learn from this analysis and where we can direct this research in the future. So this is the BH X-ray binary system with a neutron star running around the B star with extended disk. And when the neutron star passes the disk, it can accrete the matter, and we see the bright X-rays. When the neutron star moves away from the disk, it enters the quiescent state, and we usually do not detect the pulsation from the neutron star. But let's have a bit closer look on the details of the system, because I will be talking quite some time about the geometries, so it's important so we would understand the basic angles of the system. It's the usual possibility that that the disk of the B star would be inclined to the orbital plane. And the neutron star rotational axis is inclined as well to the orbital plane in general, and the magnetic axis also can be misaligned, usually is misaligned with the rotational axis, which allows us to see the phenomenon of the pulsar. Now, when the neutron star comes closer to the B star and enters the interacts with the B star disk, we see the outburst, which are known as a type 1 outburst. So this is the closest passage to the star, the so-called periastron passage. These outbursts are known from many sources for many years. This is typical behavior of the BX ray binaries. If the disk is inclined, as in this case, and as we believe for the case of JX304-1, it is possible that the neutron star passes the disk twice during the periastron passage, and then you usually see the double peaks in the light curve during the type 1 outburst. And when the neutron star moves away from the B star, it still can keep some remnant accretion disk, but we used to believe that the accretion in this case is ceased due to the propeller effect, because essentially there is no way to feed the disk in this case. Finally, the last angle to this picture is the inclination of the observer to the system, so the angle under which the observer look at this. I will start with a description of the outburst behavior, actually, because the accretion columns today have been already mentioned. So in the case when we have high mass accretion rates onto the neutron star, we have extended accretion columns, and the matter slows down in the extended shock region by the interaction with the photons. So this is the radiative shock. What is important to mention to understand the emission from such structures as the accretion columns is a bit of the details on the processes in highly magnetized plasma. Is first that radiation in highly magnetized plasma is strongly polarized and can be described in the terms of two polarization modes, ordinary and extraordinary. I sometimes here use the notation sigma 1 for the ordinary mode and sigma 2 for the extraordinary. And these modes participate quite differently in the photon-electron interactions. And the second fact is that the electrons are quantized to the Landau level perpendicular to the magnetic field, which gives rise to these cyclotron resonances in the cross-sections, for example, for the Compton scattering. And here you look exactly at the Compton scattering cross-section in the strong magnetic field. And the few things to note that the extraordinary mode has very low cross-section in continuum and very isotropic. So these are shown different angles, and all angles for the extraordinary modes falls to the one line. And for the ordinary mode, we see the variation in angles. And when we look at the 90 degrees to the magnetic axis, we have the Thomson value for the ordinary mode. Then both modes exhibit cyclotron resonance, and the shape and the width of the resonance also depends on the viewing angle. Now, this resonance, which was already mentioned, is responsible for the formation of the cyclotron resonance scattering features in the spectrum of the new X-ray pulsars. Usually, we see these features on top of the continuum, which can be represented by described by power law with exponential cutoff, and usually is formed in the accretion channel due to the bulk and thermal comptonization. Now, this is the picture which we used to see for many years at high mass accretion rates. Well, the continuous shape still can be more complicated than just power law with the cutoff and even just with the cyclotron line. But we still received quite some surprises last year, also thanks to the NuSTAR. So we observed the known system like AO535 plus 262 and JX304-1 in quiescence. And they showed the X-ray emission in quiescence and the dramatic spectral change compared to the outburst spectrum. So they showed mimicking the behavior of the known persistent low luminosity source X Persei with two components. And maybe I just note that there was the wide discussion regarding X-Persei. What is this deep? Is it a cyclotron line or not? And maybe I use it also this opportunity to note that, well, as I will try to show, not all features, absorption features at high energy part of the spectrum should be interpreted as a cyclotron line. It can be just due to the complicated continuum formation. By now we know quite a number of sources that show similar behavior in quiescence. And all of them, you can just know that all of them have quite high spin periods, which allows them not to enter the propeller regime. Now at quiescence, at low mass accretion rates, instead of the accretion column, we allow the matter just to reach the neutron star surface, and all the breaking happens in the very thin layer of the neutron star atmosphere by Coulomb collisions. In the electrons stopping much faster, electrons of the appalling ionized flow stops much faster at the top of the atmosphere, forming the hot layer, and the protons can penetrate much deeper to the atmosphere, and usually the proton penetration depth would be one of the important parameters for modeling. We have still quite simplified, but more or less realistic model for this case. So we assume that the neutron star atmosphere under the polar cap is the highly magnetized slab. And we use for now only the parameters of the mass accretion rate, polar cap radius, and the surface B field value to calculate the polarized radiative transfer in the atmosphere, allowing for the partial energy and frequency redistribution. And the atmospheric structure is calculated from the energy balance and based on the hydrostatic equilibrium. These are the first results which we obtained. The first atmospheric structure shows that the top of the atmosphere is strongly overheated. So you see this is almost 30, it's higher than the 30 kilo electron volts, followed by the region with a high temperature gradient, and the cooler is a thermal interior. And the spectra which we obtained from this kind of structure looks indeed two component-like, with a thermal hump brought up strongly by the extraordinary mode, which, as you remember, has very low cross sections in this energy band. And the second hump is essentially formed by the wings of the cyclotron line, which are very strong and very broad, and they are mainly formed in this non-homogeneous part of the atmosphere with high temperature gradient. In the end, the cyclotron line is also much wider and broader than we usually observe it for the high mass accretion rates, just due to the highest temperature at the top of the atmosphere. I don't have too much time to describe this slide in details, unfortunately, but maybe we can just focus on the polar diagrams. And again, for the extraordinary mode, this yellow and orange lines at low energy band show kind of fan beam emission. So this would be the emission profile. Well, not isotropic, but isotropic-like. And the ordinary mode has more pencil beam diagram in these energy bands. And then below and above the cyclotron resonance, which is shown in gray, you see the strong redistribution of the photons. So we see the result of a strong angular redistribution when the photons can leave the atmosphere under the big angles to the magnetic field, because at the lower angles, they are locked in the resonance still. So what do we do with this next to obtain the observed spectra is we should put this emission profiles and the spectra on top of the sum emitting structure. So this you see the principal geometry. Two poles have the two polar angles and the azimuthal distance between them, azimuthal angle. In principle, none of this configuration has to be symmetric, and we see the strong evidence from pulse profiles at higher luminosities that this likely that configurations are not symmetric in general. And use the relativistic reflection projection code by Sebastian Falkner to obtain the projection of the neutron star into the observer plane. Here the poles are enlarged because if I put them in the real size as they are from the modeling and also from the estimate from the magnetospheric radius, they are almost not visible. So please remember that they were here. because here they are not visible again. This is the result of the simulation, a combination of the radiative transfer with a ray tracing code to obtain the pulse profiles and the spectra at the different rotational phases. And maybe you can just note that this part between the two humps is showing the strong phase variability. That's why sometimes it also can be taken for the cyclotron line. Now we combined all our spectra at the different parameter ranges and in one table model and applied to fit the GX304-1 low luminosity observation by NuSTAR and Swift XRT. And what we discovered, as you see that these two humps which we observed is essentially the thermal hump and only the red wing of the cyclotron line. The parameters which we obtained with the best fit is the polar angle of one of the columns about 70 degrees and the observer inclination of 30 degrees. This is a bit special case because we fixed essentially the polar angles of two columns with respect to each other. So the one polar angle determines both of them. So this is symmetric location, but we allow for the azimuthal asymmetry, which seems to have more dramatic effect. And now when we study the parameter probabilities with MCMC simulation, we see that there are actually two perfectly, well, not perfectly, kind of symmetric solutions here and completely no constraint on the azimuthal angle between two columns, which is in this case is phi AC2. So let's see whether the phase result spectra helps with that. And spoiler, they do. For example, when we have a look at the pulse profile of the low luminosity observation, just for the comparison, I put here the pulse profiles of also GX304-1 at high mass accretion rates. You see that the structure of this pulse profile is much more complicated. I believe it's not only due to the flux level, which is much higher, and we not resolve the structure here, but also the extended accretion columns allows for the much more sophisticated beaming than just the pole emission. And we applied our model on the phase resolved spectrum. And basically got the second solution, which we saw already when the one pole was at 30 degrees and the observer inclination now is at 85. And having a look again at the parameter probabilities, we see that two solutions still remain here for the observer inclination and the pole and the first polar angle, but we can constrain the azimuthal distance between the poles much better. So it is about 200 degrees, 20 degrees deviation from the symmetry. Now, how to understand these two solutions? Well, just a quick look. If we imagine that this is the plane in which the rotational axis and the observer line of sight lays, and we catch it in the moment when the magnetic axis passes this plane, then at the phase 1, we see the pole 1 and the angle θ1. And at the phase 2, we see the next pole, which is coming closer now to the observer and the angle θ2. Now, if we swap this axis and have a look at the second solution, we see exactly the same angles between the first pole and the observer line of sight and between the second pole and the observer line of sight. So essentially, these are undistinguishable solution, and unless we have some new information about the inclination of the orbital plane, for example, we cannot say which one of this is the true one. So let me just conclude. This talk was about the modeling of the quiescent state of the BX-ray binary with highly magnetized, slowly rotating neutron stars. And we are trying to constrain some fundamental parameters using the physical modeling. And for exactly GX304-1, we obtained the following angles of the 30 degrees and 85 degrees for the observer inclination and one of the poles, or vice versa, as I mentioned, and about 20 degrees azimuthal asymmetry between the poles. Now, in principle, the inclination of the observer of the orbital plane to the observer can provide us with more information being combined with known inclination of the neutron star to the observer, which we might be able to determine, for example, the inclination of the rotational axis of the neutron star to the orbital plane. So this is the future research. And a bit more on the development, we still plan to include the polarized propagation of the radiation in the magnetosphere to obtain the observed polarization signal. And we recently received the new 180 kilosecond observation of GX304-1, thanks to the NuSTAR team. And we hope that it will help us to constrain the high energy emission, because as you see, the cyclotron line is essentially not reachable. So the higher we can go in energies, the better. And we are also looking forward to the HEXP mission. Thank you very much for the attention.
So hi everyone, my name is Jingyi Wang. I'm a first year grad student at MIT working with Aaron Kara. Today it is a pleasure to share with you some results on black hole X-ray binaries using reverberation mapping with the aim to better understand the disk-chronojet connection in accreting black holes. We know black hole binaries go through different accretion states in their outburst. In this hardest intensity diagram, we can see the hot state is when the X-ray emission is dominated by this hot polar-like emission thought to come from some hot plasma that we call the X-ray corona. In the power spectrum, we can see the peaky features called the quasi-periodic oscillations, or QPOs. In the radial, a compact, mildly relativistic and steady jet is commonly observed. The black hole binaries climbs up in the hot state until it starts its state transition through the intermediate state, along which there is usually a transient and highly relativistic jet at the so-called jet line, and the power spectrum still show the peaky QPOs, and the flux spectrum has both the disk and corona emissions contributing. Then in the soft state, the jet is quenched, and the thermal disk component dominates in the flux spectrum. There are many remarkable questions we want to answer. First of all, what is the nature of this X-ray corona? Some people think it is it crowns the inner part of the accretion disk, while some believe it is very closely related to the jet and can actually be the base of the jet, and some think we actually need a combination of both. Figuring this out is challenging, but also very important because it is crucial if we want to have reliable black hole spin measurements. Another important question is, what is the state transition mechanism? One popular idea is that in the hot state within the outer standard sync disk, there is this inner Hall flow that serves as the corona, and the inner Hall flow collapses during the state transition, along with a less truncated sync disk. But this model is challenged by some analysis suggesting the disk is not truncated in the bright hot state. Also, the corona nature is still debated, and it can sit at the launching point of a jet, so on the vertical axis of the black hole, instead of being this inner Hall flow. To answer these questions, we need to measure the geometry of the disk corona system, and this is where reverberation mapping method shines. The interaction of photons from the corona and materials in the accretion disk produces a reflection spectrum. Reverberation is the time delay caused by the light travel time difference between the primary corona emission and the reflection component that travels this extra distance. And so how can we detect such a lag? This is a digit model ratio plot when you fit the flux spectrum to a power law, which approximates the corona emission. Then you can see the red soft band is dominated by this reflection component, and the gray hard band is dominated by the corona emission. Then this means we can extract light curves in these two energy bands and measure the time lags between those two. And that time lag can then tell us the size of this X-ray emitting region that causes reverberation. We can take a look at a typical measured lag versus Fourier frequency spectrum. we can see the negative soft lag marked by the red bar at relatively high frequencies. If we calculate the energy resolved lag versus energy spectrum, we can see the soft axis and the broad iron line features just as in the flux spectrum. Therefore, the nature of this negative soft lag is confirmed to be reverberation. In addition, we observe at low frequencies, shaded in blue, a ubiquitous hot lag, and it has a featureless shape in the lag energy spectrum. This is thought to be related to the intrinsic variation of the coronal emission spectrum, resulting from, for instance, a mass accretion rate fluctuation. But the exact mechanism is still not well understood. We should take a look at an important result from reverberation on this superstar we talk about a million times today, MAXI J1820. The figure on the left and also the arrows show you how the source traveled in its 2018 outburst in the HID. Reverberation analysis has been done in the rainbow-colored observations. In the lag frequency spectra in the middle, you can see the low frequency hot lags and the high frequency soft lags. And those negative soft lags frequency are marked by the horizontal lines at the bottom. And just a reminder, those soft lags are due to reverberation. The main finding in this paper was that in the hot state, the soft reverberation lag happens at higher Fourier frequencies, and the lag also becomes shorter and shorter. And this could either result from a change in the inner edge of the disk or a change in the coronal geometry. However, from the fact that the red wing of the broad iron line shape still stayed the same, the inner edge of the disk should also stay the same. Therefore, Aaron put forward the idea that the corona contracts in this hot state plateau. As you can see in the HID, the good news is thanks to NICER's day-to-day coverage of this source, it caught the super bright hot to soft state transition, which happens very fast in just a few days. And in the past, people have only performed reverberation analysis in the hot state because that is when the coronal emission dominates and you have enough variability to measure the time lags. But this precious data set reached 10 to the 4 counts per second, really enabled me to decided to extend our reverberation analysis to the state transition for the first time. I also want to highlight that during this state transition, radio astronomers have observed a transient radio jet at the jet line, so that is consistent with the state transition paradigm I talked about earlier. We can firstly look at the error line evolution because that line profile could phenomenologically tell us something about the disk coronal geometry. This is the digital model ratio when you fit the flux energy spectrum to disk BB plus power law model, in which the disk BB is a multicolor black body emission from the disk, and the power law can approximate the coronal emission. So the axis here is the broad iron line shape. We see the narrow core dropping down in the hot state, just as what Erin saw in her 2019 paper. Then during the state transition, very surprisingly, we found if you compare the purple spectrum in the state transition to the yellow spectrum at the end of hot state, you can see the blue shift very prominently. This extra blue shifted components, we try to fit the NICER and NuSTAR spectra and found that can be modeled by returning radiation or emission from the plunging region. But what is very clear is that during this state transition, the red wing of the line does not increase as would be expected in the popular state transition model, where the inner edge of the disk moves inwards in the state transition. These are the lag frequency spectra. In all epochs, we detect high frequency soft lags due to reverberation, whose frequency ranges are again marked by the horizontal lines at the bottom. With the chosen epochs, first we confirm that during the hot state, reverberation happens at higher and higher frequency and the lags becomes shorter, as shown from the red to the yellow epoch. And then for the first time, we see when the transition starts in the purple lag spectrum, the soft reverberation lag frequency surprisingly decreases, and we also have longer lags compared to the yellow epoch at the end of hot state. So it looks like an opposite behavior in the state transition compared to the hot state. And the longer lag implies a larger disk corona region that causes reverberation, and that can very likely imply an expanding corona. So with the great quality lag spectra and the physical reverberation model called RailTrans developed by Adam and Gula, we fitted the time lags in different epochs. And here is an example of the quality of fit we can get when we fit the lag energy spectra in 4 different Fourier frequency bands. This is the yellow epoch at the end of hot state. The time lag fitting result is that the longer reverberation lag can be explained by our model with an expanding corona. Here I show you the X-ray corona heights in the 5 different epochs in the state transition, and AMI radial flux density is shown in red, both as a function of time. So the fitted X-ray corona height increases from about 30 gravitational radii to hundreds, while in the radial, they are launched a ballistic transient jet at the radial flare, about 5 days lagging behind the initial X-ray change. I also want to point out that even though we were unable to find reverberation lag in the NuSTAR data, we can always compare results with NuSTAR spectral fits. In Douglas' 2019 paper, he talked about earlier, he fitted the NuSTAR spectra in the colored epochs in the HID with a double lamppost model, which means there is both a lower and an upper lamppost corona illuminating the disk. And he found that the inner edge of the disk is about 5 gravitational radii, which is consistent with our results by fitting the NICER time lags. Moreover, the lower panel shows the evolution of the 2 lamppost heights, and you can see the height of the upper lamppost decreases in the hot state and increases towards the state transition. This evolution is very much consistent with the corona height evolution we found by fitting the NICER time lags. But in the end, we have only seen this reverberation lag getting longer in state transition in one single source, MAXI J1820. And then the next question is this behavior common in black hole X-ray binaries or not? NICER, since its launch in 2017, has already observed more than 20 black hole binaries. So we are well placed to do a systematic reverberation lag search in the entire archive. So I built this so-called reverberation machine. And the search result is that we are able to increase the sample size from previously only 2 to now 10 sources by a factor of 5. This means reverberation is a very common process and can be detected when the data quality is sufficient. Moreover, here, this is the one plot I wish you can remember after this talk. These are the reverberation lag amplitudes in the HID for all the 10 sources, where redder and bigger points mean the lag there is longer. So you can clearly see that the reverberation lag is generically longer in the state transition compared to the hot state. Instead of the HID, a more quantitative way to present the reverberation lag evolution in 10 sources is with the so-called power spectral hue, which is fundamentally a measure of the shape of the power spectrum, just like we can quantify the shape of the flux spectrum with the hardness ratio. And the 2 power colors are defined as the ratios of integrated powers in different Fourier frequency bands, just as shown here, and the paths taken around the power color diagram, namely plotting power color 2 versus power color 1 as a sample of black hole binaries evolve is highly consistent. So displaying this wheel shape. As the schematic on the right shows, an outburst will start off from the red dashed line and travels clockwise through the hot state, intermediate state, and soft state, and then travels counterclockwise back to the hot state. So with the idea of hue introduced, here I'm plotting all the reverberation lags we detected, their measured lag amplitudes as a function of this power spectral hue, and different colors represent the 10 different sources. As the outburst takes place, the hue goes from about 0 to 140 degrees in the hot state, and then it is the hot intermediate state shaded in gray, then it's the soft intermediate state shaded in blue. Then we are able to see that the reverberation lag amplitude decreases in the hot state and increases in the state transition as the arrows show. This is very exciting because this plot clearly shows that the longer reverberation lag in state transition is a generic behavior of black hole X-ray binaries, not just in MAXI J1820. And this should be taken into account and be explained in state transition models. In addition, if we read the absolute values on the y-axis, we can see that lag amplitude increases by a factor of 10 from about 1 millisecond at the end of hot state to 10 milliseconds during the state transition, which would correspond to a light travel time of 10 gravitational radii to 100 for a 10 solar masses black hole. And this is of the same order of magnitude as the X-ray corona height we found when we fit the time lags with the reverberation model real trends in MAXI J1820. Here I'm plotting against hue, but here the y-axis is the QPO frequency, which as we know for 20 years keeps increasing during the hot state and intermediate state. The leading model for these QPOs is the relativistic precession model, in which the QPO fundamental frequency is simply assumed to be the length ring precession frequency at some characteristic radius, perhaps the disk truncation radius. Therefore, under this model, the increasing QPO frequency can be naturally explained if the disk inner radius moves in the hot state and state transition. So the QPO frequency evolution is thought to be an evidence supporting the collapse inner hot flow model for the state transition. However, something very interesting shows up when we plot the reverberation lag amplitude versus the QPO frequency. If the QPO arises simply from this precession of the inner hot flow that serves as the corona, then we always expect to see that if you have a smaller inner hot flow, the QPO frequency would be higher and the reverberation lag would be shorter. This is indeed what we observe in the hot state, but it is not what we observe in the intermediate state or state transition. So what does this mean? It seems to suggest that the corona is both radially and vertically extended. Let me elaborate on that more here with the cartoons. If the QPOs is coupled to mostly the radial extent, which is marked by the orange arrows, the higher and higher QPO frequency means a shrinking radial extent of the base of the jet, and the reverberation lag can happen. On the other hand, if the purple regions mark where the reverberation lag can happen, then you can see the reverberation lag would depend significantly on the vertical extent of this base of the jet or the corona. Finally, let me summarize the disk corona jet connection we infer from reverberation mapping analysis. So in the bright hot state, the corona contracts, and in the radial, the steady compact jet fades. And in the state transition, the X-ray corona expands vertically to hundreds of RG, while in the radial, a transient highly relativistic jet is detected several days later. Therefore, our results suggest that the X-ray corona can very likely be the base of the jet. Moreover, the state transition might not be marked by the change of the inner edge of the disk as in the collapsed inner hot flow model, but instead marked up by the corona expanding vertically and launching a jet knot that propagates along the jet stream at relativistic velocities, and that jet knot becomes radial bright several days later. I'll leave my summary here, and I'm happy to take questions. And finally, I sincerely want to say happy 10 years anniversary to the NuSTAR and the NuSTAR team.
Thank you. Are there any questions? Quick questions. If not, let's move on to the next speaker. We have Renee on the line. Go ahead.
Okay. So my name is Renee Ludlum, and I am an Einstein postdoctoral fellow at Caltech. I'm going to be talking today about some of my recent work, which is on radius constraints from NICER and NuSTAR observations of the neutron star low mass X-ray binary known as Cygnus X-2. Now, just some brief background in case there's anyone in the audience who's unfamiliar. Why is it important that we're studying neutron stars? The matter inside of a neutron star exists in an ultra dense cold state that we are unable to reproduce in Earth-based laboratories. As a result, the only way to understand how matter behaves under these sets of conditions is by observing neutron stars. Here is showing a very simple cross-section schematic of a neutron star where the outermost 10 to 20% is the crust region. In this region, the density is less than that of an atomic nucleus, or about 3 times 10 to the 14 grams per cubic centimeter. We have a pretty good idea of how the matter is structured and behaving in this region, but it's not until we enter the core of the neutron star, where the density exceeds that of the atomic nucleus, sometimes several times over, that our understanding of the composition really breaks down. We don't know if we have some uniform matter of nucleons within this region, or if we're able to generate some kind of exotic matter like hyperions or even kaon condensates, or if the nucleons break down into their quark constituents and some kind of strange quark matter arises, or even a combination. The only way to know what the internal composition of a neutron star is by determining the equation of state. This is how the pressure relates to the density in this centralmost region. This in turn sets macroscopic qualities like the mass and the radius of the neutron star. So by determining neutron star masses and radii, we can backtrack the equation of state. So here's just showing the mass radius plane for neutron stars with some different theoretical equation of state tracks traced out. This is not comprehensive of all proposed equations of state, but meant to demonstrate the behavior based on the assumed internal composition and how the matter is interacting. Blue is showing nucleonic matter, green is showing a combination of nucleons and exotic matter, and purple is showing strange quark matter. This gray region in the top left corner is excluded. This is because this is where causality becomes violated within the neutron star, where the speed of sound exceeds the speed of light, so your neutron star is no longer stable to perturbations. We have a number of mass estimates from binary neutron star systems, and these agree with most of the proposed equations of state, if not all of them. But it's not until we get to the most massive neutron stars that have been measured to date, such as pulsar J0740, that we begin to rule out equations that cannot produce a stable neutron star above 2 solar masses. Now, there are still a number of equations that agree with this more massive neutron star measurement, that it becomes clear we need to start focusing on radius constraints. This is because the radius is a slow varying function over a large range of mass for most of the remaining equations. One way that I have been doing this is by studying disk reflection around these neutron stars. This is because the accretion disk must truncate at the surface of the neutron star, if not prior to it. And even if
hold on a second.
You should
We're having trouble with the audio.
Okay, am I back?
Yeah, you're back. Go ahead.
Okay. So because the disk must truncate at the surface of the neutron star, if not prior to it. And even if the radius of the neutron star is smaller than that last stable circular orbit in the accretion disk, we're still able to get an angle at the equation of state by ruling out equations that would predict a more massive radius than what we're inferring from these disk reflection studies. We can also learn more about the properties of the disk itself, like its density, and also more about the neutron star, like getting limits on the magnetic field strength. So I know that people have covered reflection, but I'm going to just briefly recover it for neutron star systems. So it's similar to black holes, where you have your accreting compact object surrounded by a geometrically thin, optically thick accretion disk. And then you have hot electrons in a coronal region that produce hard X-ray emission. We see the direct emission from the corona and the accretion disk, but some of these hard X-rays can irradiate the disk, be reprocessed and re-emitted in what we refer to as the reflection spectrum. So you will obtain this overall spectral shape shaped by the accretion disk, those hard electrons, as well as the reprocessed emission, with this prominent feature between 6 to 7 keV due to iron K-shell fluorescence. But you can also have in these systems that the neutron star itself, or a boundary layer region that may exist between the inner edge of the disk and the neutron star surface, can emit in the form of a thermal component that will irradiate the disk, be reprocessed, giving an overall different spectral shape, but the reprocessed emission still has that prominent iron line feature between 6 to 7 keV. Now, this iron line is important because it's intrinsically narrow line emission that is broadened by different effects within the innermost accretion disk. Due to standard Keplerian motion, you get a 2-horn profile. Then due to the relativistic motion within the disk at which the rate that the material is moving at, some of this is beamed into and out of the line of sight, giving the overall skewed shape. Then due to the large gravitational potential well in which the material is sitting in, this is overall gravitationally redshifted down to lower energies. So the degree of broadening that we're measuring in the red wing, or how extended this line emission is to low energies, tells us how close we are to the compact object. Additionally, from looking at the blue wing of the iron line, we can look at the inclination of the system. This is because your Doppler effects are going to become more prominent as you switch from a face-on to higher inclination. So you're going to broaden the line out to higher energies. Now, specifically in this work, I was looking at Cygnus X-2. This is a persistently accreting Z source, and this just refers to a characteristic shape traced out on the X-ray color diagram shown here, as it transitions from a hard state in the horizontal branch to a softer state in the flaring branch. We can also look at these systems in terms of their hardness ratio versus intensity, and in this case, Cygnus X-2 traces out a backward C shape. It does have optical studies that have been performed that determine the binary orbital period is about 9.8 days at an inclination of 63 degrees. And from ellipsoidal light curve modeling, it has a determined neutron star mass of 1.71 plus or minus 0.21 solar masses. So this makes it a great candidate for going and getting those complementary radius estimates from disk reflection studies. Particularly here, I used NuSTAR. This is NuSTAR's 10th anniversary. So we used NuSTAR to look at the hard X-ray coverage. And then we complemented this with NICER's lower energy passband to create this broad X-ray band pass, and also to achieve more photons in the iron line region to really do this robust determination of the inner disk radius. Now, NuSTAR observed the source on 3 occasions, once in 2015 and 2 more times in 2019. And you can see in the hardness intensity diagram that it traces out that characteristic C shape from the horizontal branch down to the flaring branch, though there's an overall change in intensity between the 2 different observing epochs. And there's also a lot of variability within each of these observations. Now, these 2 2019 observations were taken simultaneously with NICER. And here is showing the simultaneous NICER and NuSTAR light curves during these observations. NuSTAR tracing the harder X-ray emission, while NICER's tracing the soft X-ray emission. And you can see how variable the source is, which is why it was so important that we had simultaneous observations. Now, when selecting our data for the spectral analysis, I chose spectra that have greater than 1 million counts per spectrum. So that's per NICER, per NuSTAR FPM-A, and per NuSTAR FPM-B. So this left us with 3 different spectral states: the normal branch from observation 1, the vertex from observation 2, and the horizontal branch from observation 3. And here is just showing the ratio of the data to a simple continuum model in the iron K region of the spectrum. And you can see this broad iron line component in each of these different branches with the NICER and NuSTAR observations. And again, this choice was done for signal to noise purposes to really get robust spectral constraints when applying reflection models. Now, for spectral modeling, I started with 2 separate continuums. First, a 3-component phenomenological model of an accretion disk, a single temperature black body, and power law component. Then a more physically motivated model of an accretion disk and a thermal comptonization. From there, I applied reflection models that matched the input continuum. So for the first case, we use Relzel NS, which is a self-consistent reflection model that is tailored for the thermal emission coming from a neutron star. In the second case, I used RFX-Compt to approximate the reflection from that comptonization component and then relativistically blurred it. When doing so, there's still the presence of a 1 keV feature, and this has been reported in literature in the past, and it's not being picked up by reflection. So it's not coming from the inner disk. It's likely coming from an area farther out, either from a collisionally or photoionized plasma. So we model it 2 different ways, using a simple Gaussian and even using a collisionally ionized plasma model. And the results that we find is that the inner disk radius agrees with being very close to the neutron star, no matter how we choose to fit this 1 keV feature or our choice in reflection model and continuum model. We also find that the inclination agrees with that optical estimate, which is encouraging. So regardless of our various spectral modeling choices, our accretion disk is close to the neutron star in each of these branches. So what does this mean when looking at constraints on the mass radius plane? Here's the mass radius plane again with those different theoretical equation of state tracks traced out. Now I had shown the values that we had obtained in terms of gravitational radii, which is related to the mass of the compact object. And since Cygnus X-2 has an estimated mass, we can convert this to a physical unit. And here's the region this traces out on the mass radius plane. So we have an upper limit of about 19.5 kilometers at the high mass end and 15.3 kilometers at the low mass end. So this is a very conservative estimation shown here. And we can compare this to the current state of the art methods and measurements that have been done for different neutron stars, such as NICER pulsar light curve modeling of that first source that NICER had published on, which is pulsar J0030 for 2 independent groups, the Illinois-Maryland group and the Amsterdam group. Then there's the second pulsar that was modeled with NICER data. And this is that most massive pulsar, pulsar J0740. Then finally, we can compare to the constraints that have been obtained from binary neutron star mergers from gravitational wave events. Now, in order for an equation of state to be viable, it has to pass through all these different measurements. And each of these different methods have their own sources of systematic uncertainty. So while doing reflection modeling doesn't rule out an equation of state on its own yet, it can provide an independent check of constraints on the mass radius plane when compared to these other state-of-the-art methods, and can ultimately help in narrowing down the allowed region for the equation of state for ultra-dense cold matter. And I'm hopeful that in the future, with the new technologies and missions that are going to come online, that we're going to have better statistical constraints and really be able to push down this upper limit that is shown here from disk reflection modeling. But when doing the overall spectral modeling that I had shown, there are other components within the models that can provide estimates of various emission radii. So we can also determine the inner disk radius from just that disk black body component that was present in both of the different spectral models. And from this, we get an inner disk radius about 15 to 62 kilometers. And this has huge uncertainties, and these are largely driven by the distance estimates that are available in the literature at the time. So this is anywhere from 6 to 12 kiloparsecs to the source. We can also determine the emission radii of that single temperature black body component. And if we assume that's coming from spherical emission, we get a radius of emission from 4 to 8 kilometers. Now, this is way too small to be coming from the surface of the neutron star, but it instead suggests that instead of spherical emission, it's coming from a narrow banded emission region that is akin to what we would expect from a black body or a boundary layer. And if it's coming from the boundary layer, we can assume that it has a height that's roughly 10% of the radial extent. And this gives us a much more reasonable estimate of about 13 to 27 kilometers. Now, there's another way of estimating the radial extent of the boundary layer that was laid out in Papin-Sunyaev in 2001, and it just depends upon the mass accretion rate of the system at the time of the observation. So by estimating the mass accretion rate from the fluxes that we observed, we get a maximum radial extent of the boundary layer anywhere from 11 to 91 kilometers. So this is important to remind you that this is a 1D approximation. So it's not taking into account any kind of spreading in the vertical direction on the surface of the neutron star. It's also not taking into account any differences in viscous effects as the material is dissipating on the surface, or even the rotation of the neutron star. So this can all impact this measurement for the maximum extent of the boundary layer and bring this into agreement with the other measurements. And as a reminder, here is the upper limit that we obtained for inner disk reflection of an upper limit of 19.5 kilometers. So using these different components can act as an independent check of the qualities that we are inferring, and can also help to build up a picture of what the geometry looks like in this system. So just to quickly conclude, regardless of our various spectral modeling choices, the accretion disk remained close to the neutron star in each of the branches that were observed with NICER and NuSTAR. Additionally, the upper limit on the radius that we obtained for the neutron star from disk reflection modeling can provide an independent check of the constraints on the mass radius plane when taken in comparison to other state-of-the-art methods. So thank you for your attention. I'm happy to take any questions.
Are there any questions for the speaker? Yes, go right up to the mic.
Yeah, thanks for a nice talk, Renee. I was wondering what assumptions you make about the structure of your corona and how it illuminates the inner accretion disk, and whether that turns out to be an important error term in the inner radius of the accretion disk.
Yeah, there's no built-in kind of geometry with the illumination. It's not like assuming a lamppost model in it. There are some calculations that I can do to further decide like what exactly the structure is. I know that it's kind of described a bit in the paper that came out earlier this year by Javier Garcia and Dowser and myself about how the model is constructed, but it's not assuming a lamppost geometry.
Okay, sure. And do you have an emissivity parameter then in the model that's kind of a proxy for that?
Yes, there is an emissivity parameter in the model. Yeah, and I can definitely go back and try to do the calculations and figure out what kind of geometry it is giving us. And, you know, actually, now that you brought it up, what we do find with a lot of these systems is that we're inferring a lower emissivity parameter than what you would typically expect. So it's not just that value of 3 for flat spacetime. And that lower geometry likely indicates, or the lower emissivity index indicates that we're likely illuminating not directly above it, but kind of at an angle that's kind of closer to where the disk is, if that makes more sense. So it's almost indicating that it would have a flared shape.
Okay, great. Yeah, that's interesting.
They have another question coming. Quick one.
Okay.
Thank you.
Yeah, quick question. Great talk, Renee. Thank you. One more method is by fitting neutron star atmospheres to quiescent LMXBs, and you can only do that if you know the distance. So the way we've done it in the past is in globular clusters. Does that add any more, or does that constrain anything any more than these methods? Have you made any comparisons?
I haven't done a direct comparison here because what you're referring to is the crustal cooling models of neutron stars. And there's a lot of degeneracy in there between the mass and radius that are inferred. Yeah. And in a lot of those systems, you don't know the mass. So there's a huge error circle between those. So I was just comparing to like the best state of the art that we have right now. That's maybe at the 10% level. Those are a little bit higher. And I'm hopeful that in the future, you know, with the coming online of Athena, there are going to be more of those neutron stars that can do those crustal cooling techniques, and we can get better statistical constraints that way as well.
Great.
Okay, thank you very much. Let's thank all the speakers and go on to the next session.
Okay, yeah, thank you so much for having me. So while I share my screen, here we are. So can you see my screen now? Yes. Awesome, thank you so much. Yeah, so thank you for having me today. I'm gonna try to give you a little tour about the huge impact of NuSTAR observations in the world of transients. And I will focus on stellar explosions because I know speakers after will cover other parts of the transient zoo. So in the world of supernovae, we basically have two big problems that have to do with what happens before. In very rare cases, we can actually tell with confidence what type of star has exploded. And in many, many cases, basically all, we can say what that star was doing the last 1,000 years. And then we also have a huge problem after the explosion happens in telling people what is left behind. Did we produce a neutron star? Did we produce a black hole? And today I want to share with you, taking as an example two explosions, 2014 C and 18 COW. I want to share what the impact of NuSTAR on both sides of the problem, what happens before and what is left behind after the explosion. So let's first focus on the first half of the question. So how do we get about learning what happens in the last hundreds of years before stellar death? This is a place where theory is not able to provide much of a guidance, and observations are actually leading the way here. So we have three basic ways we can learn about what a star does right before dying. And the first is just by observing what the star is doing. And in here, I'm referring to optical wavelength. So we look at that part of the sky. We have images now thanks to our surveys, and we see what the star was doing. The second way that we have is by getting on target very, very, very early with spectroscopy right after the explosion, and use the fact that the light from the stellar explosion is ionizing the medium, and the medium recombines, telling us its composition, telling us its velocity. So giving us information about the composition of the star right before explosion. And the third way, which is the one that is the most relevant for us today, has to do with the shock interaction. And the concept is pretty easy. So every time we have a stellar explosion, this shock is not propagating into vacuum, but instead is propagating through a medium that was shaped by the mass that was lost by the progenitor. And this is a very well-known and well-studied ways to accelerate particles. So this shock goes through the environment, accelerate particles that leads to copious radio and X-ray emission. So the idea here is the following, that if our star was not well behaved and produced a number of eruptions before stellar death, as we are finding right now, then the shock, as it propagates through this environment and its emission, would keep memory of this very, very disturbed environment. And by studying the X-ray and radio coming from the shock interaction with this circumstellar medium, we can actually learn about these eruptions of the star. Another way to put it is that using the shock of a stellar explosion, we are actually in the position to have for free a fantastic time machine that takes us back into the life of a star. The beauty of this method is that the shocks of these stellar explosions are extremely fast. They are 100 to 1,000 times faster than the typical velocities at which we release matter before stellar death. And that means that at every time t after stellar death, the shock is catching up with material that was ejected by the star a fraction of time. It was 100 times, 1,000 times t before death. So if I'm careful and I do a modeling of my X-rays and radio from shock interaction for 1 year after explosion, what I'm sampling is basically the medium that was created by the star before dying in the centuries before death. So it gives us this particularly beautiful window into the life of massive stars at the very, very end. This is exactly what I'm going to talk about, and I'm going to show how NuSTAR observations of this shock interaction with the medium actually really helped us advancing our understanding of what the stars do in the last centuries, which is not what I was taught during grad school. So here is a beautiful image, maybe one of my favorite images. This is the NuSTAR image of a supernova 2014C. And here is a hard X-ray image, of course. And it's particularly close to my heart because this is the only supernovae that we were able to follow for 7 years with NuSTAR, coordinated NuSTAR and Chandra observations. So we were really able to follow the evolution of this shock interaction with the medium. Also, I wanted you to realize it's just a 30 kilosecond exposure. This is a very bright source for NuSTAR. So let me explain in a second why NuSTAR observations are so important when it comes to studying shocks of young supernovae. So the typical problem that we run into as X-ray astronomers studying supernovae is that typically we only have the soft X-rays. So we cover, when we are lucky, we get the soft X-rays. So we cover 0.3 to 10 kV. And the spectra that we expect from shock interactions are typically Bremsstrahlung spectra with temperatures that are above the 10 kV of the soft X-ray instruments. So we are always, we've been always stuck with this issue of not being able to tell what temperature is the emission at, and also that correlates a lot with our capability to even say something about the absorption. So by combining NuSTAR and a soft X-ray instrument like Chandra in this case, we can actually find a solution for this system. So we are able to say what is the temperature and what is the absorption. And at this point you might ask, okay, why do we care about it? The reason is that the temperature maps into the dynamics of the shock. So what is happening is that we are converting kinetic energy from the shock. So the shock is converting kinetic energy into heat. So this temperature is physically related to the shock velocity. So if we do a good monitoring and we can sample the temperature evolution with time, what that means in practice when it comes to the modeling is that we can obtain constraint on the dynamics of the shock. So we know where the shock is, what velocity the shock is as a function of time. If we do that, and that means we also have information about the absorption that is telling us how much matter is in between us and the explosion. And for stellar explosion, what happens is that, of course, we do have stuff in the Milky Way, we have stuff in the host galaxy of the transit that has totally unrelated to the supernova, but in most cases, we have a lot of material that was produced by the progenitor before death. So we get information about, independent information about how much mass was lost by the star before death. So this is the context. And with this context in mind, now we can have a look at the beautiful observations of 2014C. So since it's a hard X-ray crowd, I can afford to show you all the beautiful spectra. So I'm going to show you the sequence during the 7 years of monitoring of 2014C. We realized that 2014C was a bright source in the sky roughly 1 year after the explosion. And you can see a sequence of 3 NuSTAR and Chandra spectra. And you can also, and you have a zoom in on an iron K alpha line. And then we keep going with our monitoring, and here it's maybe not super easy to appreciate, but the temperature is going down. I'm going to show you later on. And also our absorption is going down. And we keep doing that all the way to this 7 years after the explosion, and here is our complete monitoring and in the hard and soft X-rays. That's the first time that we could actually do this. So let's see what we were able to learn. So put everything together. This allows us to have a very good handle on the bolometric X-ray luminosity output of this young stellar explosion. And for the world of supernovae, 10 to the 40 point something is very luminous for a normal supernova that doesn't have a jet. And thanks to this coordinated Chandra and NuSTAR monitoring, we were also able to track the evolution of the temperature with time. Always keep in mind, temperature versus time means velocity versus time for us. And we could also monitor the evolution of the absorption with time, and we could see that absorption going down as the shock plows through most of the material that was left behind by the star before death. So we were not doing that monitoring of X-rays alone, as we always do. We always try to get as many photons as possible. So we were doing monitoring across the spectrum. So while the X-rays that on this plot are the red stars are going up, the radio also was increasing for this explosion, which is highly unusual on these time scales. And at the same time, if you focus on the bottom panel, we have something truly amazing. We go from a stellar explosion that was hydrogen poor, that is the zoom in on the H alpha line, and then we build up hydrogen and we become a type 2. So basically, for those of you that are supernova people, we went from a type 1 to a type 2 over the course of 1 year. And that was the result of the supernova shock interacting with a wall of hydrogen. And thanks to our monitoring, we were able to quantify how much matter was there. Is of the order of a fraction of a solar mass. And that brought in the most important question of why that hydrogen-rich wall was there. And that has 2 potential explanations that are equally interesting in my own from my own perspective. So the first is that there are nuclear burning instabilities that we have not been considering so far, or not as we should have, that lead to the envelope ejection of these progenitors right before stellar explosion, when we are not expecting those stars to do so. And the other possibility is instead that the stars are not born alone, they're not dying alone. There is a binary companion that is helping out with the envelope ejection. So the beauty of the monitoring, the coordinated monitoring, was also the fact that from a quantitative perspective, we could not achieve a good agreement with data across the spectrum, including NuSTAR, Chandra, and the BLA, unless we broke spherical geometry. So not only we could quantify how much stuff was in the environment of the order of a solar mass or so, but we could also say that that material needed to be definitely distributed in a completely aspherical way, and we suggested a disk-like geometry. And now the question that you might have in your mind is 14C alone? So is that something that happened once, and at the end of the day, who cares if there is only one star in the sky that does that? And the answer is a straight no. Here is a busy plot where you can see on the x-axis the locations of shells of CSM that we have, of circumstellar material that we have estimated in our stellar explosions, and how much mass was contained. But there is a huge caveat here that while for the big star, which is 14C, we actually have a good handle on a lot of the physical quantities of the system and even on the geometry of the system. And that was thanks to this coordinated monitoring. This is not true for basically all the other dots that you see on this panel. So basically the message is that the universe is telling us that we have something that we are missing out on stellar evolution. And there is something very interesting happening in the last centuries in the life of these massive stars. And what we have to do is to collect more of these fantastic data sets, just like 14C, to try to understand what is behind the physics behind. So let me now jump in the second half, in the last 10 minutes of this talk, about what was the contribution of NuSTAR to the second half of the problem about, okay, let's assume that we understand when we explode, what is left behind. And this is a huge issue in the field of stellar explosions. There is no way we can go from a stellar progenitor to a stellar remnant in a self-consistent way. We do know for sure that the universe produces neutrons, at least for neutron stars, we can see them. So we can pinpoint them in our supernova remnants in our galaxy. So we do know that the universe does produce compact objects this way. And here it took 1,000 years before we could actually see down all the way to the interiors and see the compact object that is responsible for this beautiful display. But of course, this is not true for our young stellar explosion. The problem is this black cloud here that is how I picture the ejecta from the supernova explosion. So even if we produce a neutron star or black hole right away, there is no way we can have information from this compact object, simply because there is just too much matter around. And what we have to do is to wait for this matter to dilute, and eventually it will become transparent, and we might have a way to see what was produced. You might be thinking right away that maybe we could have better opportunities to see these neutron star black holes at a younger stage if we had less ejecta. For better if we were dealing with ejecta that is not spherical but is strongly asymmetrical, so that we had some paths of less where the resistance to the photons, to escape of photons, is less, so we can hope to see those photons earlier on. And this is a picture that is very relevant to this new class of stellar transients, the fast and blue optical transients that I'll be talking about in the next few minutes. So what are those? So first of all, the field is so young that we don't even agree about how to call them. So for the rest of the talk, I'm gonna call them FBOTs, fast and blue optical transients, but some people will call it FELTs, fast evolving, luminous transients. It's all over the place. But what it means is transients that reach very high optical luminosities. So this is an optical diagram. And they do so on very short time scales. So our FBOTs are the red stars in this plot, and you can see how they compare to the stripe of type 1As that allow us to do cosmology. The superluminous supernovae, they can get as luminous as the most luminous optical supernovae that we know of. And then there is a world of vanilla type 1, type 2, so-called collapsed supernovae. So the bottom line is they are fast and they get very luminous, and they span a huge range of luminosities. And that, to me, it means they are not a homogeneous class. they're just defined in a way that they seem to fall in the same box, but they're likely not. The other piece of information is that they've been always connected to galaxies with star formation. So we don't need an old stellar population. That's what it means. So if you put together the requirement of fast time scales and very high luminosity, that rules out right away the normal supernova, the way we power normal supernovae. And that is because the amount of nickel-56 that we would need to power FBOTs is so large to reach those luminosities that by that time, the diffusion time scale through that amount of ejecta would violate the their very fast time scale. So photons would not have enough time to diffuse out from the amount of nickel-56 that we need to power their light curves. And at that point, we have two options. So we have something that gets very luminous. So we need an extra term in our energy equation, and we can decide where to put it. And in the literature, you would find two options. The first is we add an extra energy term deep down in the core of the ejecta, which is the scenario that you have on the left. For the very same argument on diffusion timescale, this also means that the amount of matter that we can afford to have around that central engine is tiny. Otherwise, again, the photons will not be able to diffuse out in time. The other option is forget about a central energy source, but let me put that energy source outside. And a physical picture that you can put it in your mind would be like a shock interaction with the medium, just like we have seen with 14C. This scenario has some specific predictions. So first of all, we do expect no fast variability because the emitting region is large, is external radius. Since we are thinking about producing a lot of luminosity, basically by converting kinetic energy into radiation, that means we are decelerating a shock. So if anything, I would expect to see a slower ejecta than average, definitely not relativistic ejecta. And then the other piece of information is that this is a scenario where after the shock slams into this environment, into this thick environment, it releases the energy and then it can only cool down. There is no persistent source of energy. So we should see cooling with time. And these two options persisted in the literature for a while, mostly because these FBOTs for years were not seen outside the optical. And things changed dramatically with this transient, the 2018 COW. And I'll go fast on the non-NuSTAR properties because I do believe that the most surprising features of all was what NuSTAR found for this transient. So first of all, this is where the transient happened in a galaxy of 60 megaparsecs. That for this type of transient, it meant extremely close. We were used to find them at 10 times this distance, so like a redshift 0.1. Here we're dealing with something that is the closest event that we were able to find. We put it on a peak luminosity optical versus time, and yes, the cow is very luminous and is very fast. So it does satisfy all the criteria, and actually is very extreme even among FBOTs. But as I said, for me, the most interesting piece of the puzzle came from the X-ray monitoring. Here you have a light curve, X-ray versus time, and you have in black the soft X-rays, and then you have in color the harder part of the spectrum. But for now, just focus on the soft X-rays. So first of all, 10 to the 43 erg per second at the beginning. This is very luminous. As I said before, I was happy with 10 to the 40 point something for 2014C. Here we have something that is way more luminous than that. Those are luminosities that we have been only associated to gamma ray bursts like or tidal disruption events. And then I also want to draw your attention to how variable the emission is. So this variability that you see in the soft X-rays is real. There are flares going up and down, which is not consistent with the idea of a shock interacting with matter at some large distance. And if we place the cow in the world of the X-ray world of transients, here is a busy plot where you have in orange the tidal disruption events that we're going to hear about more later in the session. And then you have in gray the cosmological gamma reverse, and then you have the nearby gamma reverse here, the long ones, the long gamma reverse in blue. And as you can see, the cow rivals and actually is more luminous than some of the nearby gamma reverse. So this gives you a scale for how powerful the emission from 18 COW was. But again, it's a spectrum. It is a hard X-ray spectrum that for me was the biggest surprise. So this is a crowd that is extremely familiar with this type of spectra. And this is what I usually show in supernovae to supernovae conferences and transient conferences, where we are really not familiar with this type of spectra, where there is this iron line and Compton hump. So this is something that definitely the world of transients is not familiar with. And now let's have a look at the broadband spectrum of 18 COW at 7 days. So this is a spectrum where we have XRT, Swift XRT at soft X-rays, and then we have NuSTAR, and also integral at the higher energies. And as you can see, we do have power law and absolute power law at lower energies. This is extremely common, and for those that do transients, this is your typical synchrotron spectrum. Nothing really stands out. But then we had to deal with an excess of emission around this 8 kV, and then that hump. And I do remember the first time that that I saw this data, and I think Brian Greffenstadt was the first one to say, "Hey, I think this looks very much like a Compton hump that I'm used to see in the sources that I study." But of course, for us transient people, this was new, and I have to say this is the only time that transient showed anything like this. So we started thinking about what might be producing this type of emission, and really trying learning from other fields here, we came up with a solution, an explanation that is actually very physically similar to scenarios in AGNs and X-ray binaries, where we do have a source of hard X-rays sitting down deep in the core that is producing this power law. And some of that emission is reprocessed by some matter around, in our case, the explosion. And our prediction at 7 days after the explosion was that since one key difference between our system and binaries or X-ray binaries or AGNs is the fact that our reprocessing layer was the ejecta from this explosion. So our reprocessing layer was expanding on relevant timescales of our monitoring. Our prediction was that with time, that layer should lose its capabilities to reprocess radiation, and just because it is expanding. And so our prediction was that with time, we should have seen this Compton hump going away, while if the engine was still on, we were expecting the power law to be still there. And here is a sequence of spectra, broadband spectra, and you can see that this is exactly what happened. So at 7 days, there is a little bit of a Compton hump, and then there is a Compton hump, there is a tiny bit maybe at 10 days, and then we are left with a pure power law. So this is our, yes, thank you. So this is the picture that we came up with. So for 18 cow, we had to conclude that this was not a normal stellar explosion, not at all, but we had the need to invoke the presence of a central source of hard radiation that was reprocessed by outer layers. And I was extremely excited to hear that NICER was actually able to find evidence for a QPO at the level of 230-ish hertz in early NICER data of the cow. So we speculated that maybe what we were looking at was radiation that was directly related to the formation of a compact object that was the result of the stellar explosion. So at this QPO, if this QPO is really there, then in my mind, there is no doubt that it's a compact object that is behind this. So just to conclude the world of F-bots and why they are so exciting. So I emphasized 18 cow. This is the only F-bot for which we were able to find and monitor that beautiful Compton hump. But the cow is not alone. There are many other F-bots. And one thing that is becoming very, very clear is that these F-bots can be extremely luminous. And here I want to emphasize AT2020 MRF by Yuan Yao that will join us later. So they can actually be as luminous as the GRB jets. And what we found out is that if you monitor these F-bots in the radio, some of them can reach the same velocity, so they can be relativistic. So to summarize, one thing that is one important message is that these F-bots are a new class of transients that do have GRB-like, they can have GRB-like outflows. So we do need to invoke a central energy source. And the reason why I'm particularly excited about this F-bot is because it might provide us with a window on the first, literally the first days of life of a compact object. And I think that is all. I want to leave you with this a diagram, which is the way I think about the discovery frontiers in the world of transients, where we have two big areas in my mind where we can actually advance the field in the next decade or so, which has to do with what happens to the stars before dying and compact object formation. And in both cases, I'm a huge advocate for expanding our views outside the optical that dominates the world of supernovae for sure, and include all wavelength and especially hard X-rays. So thank you. That is all I wanted to say, and I'm happy to take questions.
Thank you. Questions? I have a question about the first part of your talk. So is there any idea what's causing this disk-like ejection?
Yeah, that's a great question. So one possibility is that we are dealing with binaries, and that's a great way to break your spherical geometry and have a preferred axis or preferred plane. And that was our speculation, that there was matter ejected as a result of a binary interaction.
Yuan, you have a question?
Yes. Hi, Rob. Thank you for the talk. So in one of Brian's recent paper, he proposed that maybe the black hole is already there, not after the stellar explosion, and there is a binary between the black hole and the core of a massive star. And maybe this is a tiny TDE that produced this collect event. How do you think about this type of theory? Mm-hmm.
Yeah. No, it's a great possibility. I don't think there is no way from a data perspective to actually say that this can be right. And from a probabilistic perspective, I think that those systems that Brian is invoking needs to exist. So I think it's another possibility to keep in mind. Yeah.
I see. Thank you.
Are there any other questions? Maybe on Slack? I don't see Slack, but otherwise, let's thank Rafael again.
Thank you.
We have a speaker in person right now, correct?
I get to see the slides over there. I'm not sure I didn't do it. Because I didn't connect it with my laptop. Can you give them to? Yeah, it's it. No, I'm not connecting my laptop, so I was given my Okay. Hello, everybody. I'm Krishnan. I'm a PhD student at the Nicolaus Copernicus Astronomical Center in Warsaw. So first, I would like to thank the organizers for giving me this opportunity to present my work on multi-wavelength study of extragalactic transients detected with eROSITA. And mainly, I will be talking about the flaring event that was detected in an AGN, which I'm working with my supervisor, Dr. Alex Markowitz, along with various other people of the German eROSITA collaboration. So I'm presenting this work on behalf of the eROSITA DET. A quick introduction. The eROSITA is the primary instrument on board the Russian-German SRG mission, which was launched in 2019. And it is more sensitive than the ROSAT in the 0.2 to 2.3 keV band. So it has 7 cameras, which has a common field of view around approximately 60 arc minutes. So it works between the energy range of 0.2 to 10 kilo electron volts. So this mission was planned for 4 years, having 8 all-sky scans and having 1 scan every 6 months. So right now, eROSITA is in the standby mode from the very late February, like stopped in between its 5th scan. So hopefully it will resume working soon. So, since it gives the all-sky scan, it is able to approximately detect 1 million of AGN sources, of which many can be different types of transients. So our group is particularly interested in changing look AGNs, which can have an increasing or decreasing flux or continuum variation, and or appearing or disappearing broad light emission lines. So we are interested in studying the different accretion flow parameters that can change with the accretion rate. For example, in the case of an ignition or a shutdown event and other cloud occultation events. So, but we also extended to the detection and study of other AGN related transients, where there can be extreme X-ray variations and cases of extreme accretion onto the supermassive black holes, such as transient that you will be hearing more about probably in the next talk, and other quasi-periodic eruptions. So we use the eROSITA survey to systematically identify the different candidate events. So for that, we first detect the candidate source by comparing the ERAS fluxes between the each scans to see if there has been any significant increase or decrease in flux. So this is mostly by eye basis, and also try to check by how much factor is this increase or decrease of fluxes. And then probably there is also some convolutional neural networking system in classification that's happening. But yes, so once we have some detection of candidate events, we try to do a follow-up study using various telescopes to get the optical spectroscopy and photometry. And then we also use the sky-based monitoring programs to get the X-ray and UV data, like the XRB-MAXI and NICER data. So yes, now we collect the database. We have the eROSITA database, then we have the data from the follow-up programs, and then we also try to check for other archival data for these candidate sources. So there has been a lot of these candidate events that has been detected by the eROSITA so far. And here I just give an overview of few of the sample sources that has been researched upon by our group. So in the first example, I have the example of an very extremely luminous ignition event that was detected, where the ERAS flux from ERAS 1 to 2 showed an increase in X-ray flux. But in the optical photometry corresponding from the ATLAS data showed that there was an increase and then a decrease in the flux, showing that this ignition could have been caused due to a sudden accretion flow. So there has been also other follow-up using the SWIFT, XMM, and NICER. And this is work that is in preparation by David Homan in AAP and Adam Malayali from MPE group. So the next source is an example where the X-ray flux seemed to be decreasing with each successive ERAS scan, and then suddenly it rebrightened, and then again it decreased in flux. So with this source had an XMM follow-up observations, 4 of them, of which it showed spectral variations where the galactic absorption column was changing. So this is a work that is led by Alex Markowitz, and I'm not going in detail about these sources because that's not the sources I am studying about. It's just to mention about the different sources that is being led by our group members. So the last, just mentioning the last source, one of the last source is when the eROSITA, we saw a decrease in flux between the ERAS scans, and we thought, okay, it should be a shutdown event. But then again, the optical light curve showed that it was actually igniting, and then we had caught it probably during the end of the ignition state. So the optical spectroscopy of this particular source showed that it had a double peaked H beta light. So yeah, you can like these are like research in progress, and probably you will be able to find them in the future, like after it's published. So talking about the main talking about the work I am doing is the flaring event detected in an AGN. So this source was detected because it was increasing in flux with successive ERAS scans, where the soft X-ray flux increased by a factor of 6 between ERAS 3 to ERAS 4. So first we thought it was an ignition event, but the recent ERAS observation, the last one, the 5th ERAS observation showed that the flux was actually decreasing, and hence it's a flaring event. So we had multiple X-ray follow-up using the XMM and NICER observations, and then we also did some optical spectroscopy for this source. So here I show you the multi-wavelength light curve of this object. So you can see the increase and decrease in flux both in the X-rays and the optical data approximately around the same time. And we have 2 XMM follow-up observations for this source. So the first observation was taken during the flaring state, and the second observation was taken after it has gone down in flux to the baseline levels. So the vertical lines shows the epochs at which the optical spectroscopy was taken for this source, and the XMM UVM also showed the flux had decreased by a factor of 3.8, meaning this source had been showing a multi-wavelength flaring. Okay, so in general, in CFERTS, observing an X-ray variability by a factor of 6 is normal. But what makes this source interesting is the spectral variability. So here I show you the 2 XMM observations, and the soft X's seems to be varying between the 2 observations. So XMM observation, okay, so both the observations shows a good fit with the double parallel model. And during the flaring state, the soft axis is fit by a very steep spectral index slope of about 2.8. And you can see that in the post-flaring state, the soft axis is now fit with a slope with a very lower slope of 2.2. So the spectra has hardened, and you can say that the soft component in both the spectra is parallel-like, but it has very dramatically with respect like in normalization and the spectral shape. So I try to fit different phenomenological black body disk BB and disk BB models, but they did not fit well with the XMM data taken during the flaring state. You can see, so here I show you a simple black body models fit to the soft axis, and the hard X-ray fit with the parallel model. So you can see that during the flaring state, it gives a very bad residuals. And in the post-flash, in the observation taken during the post-flash state, it gives a good fit with the soft axis with a black body and the hard energy with a parallel model, but it does not give me a very constrained values to the fit parameters. So here I show you the spectral energy distribution fit for the observation taken during the flaring state and the post-flaring state. Just let you know that this is a very crude fit and we have to redo the analysis. But the takeaway points for this initial fits is that we see that the Eddington ratio has decreased from the flaring state to the post-flare state by a factor of 3 to 4. And we say that the radius of the warm and the hot corona regions has increased significantly from the flaring to the post-flare observations. And the soft axis electron temperature is greater than 0.5 keV during the flaring time. So these are just initial observations that we get through the SED fits. So here I present to you the optical spectra taken for this source. So the first two spectra was taken during the flaring time of the event. SAO just right after that, and the salt 6 months apart, like exactly when during the second XMM observation taken during the post-flaring state. So what we observe here is the helium-2 line, which seems to be fading with the successive optical spectroscopy with the optical spectral line. So spectral observations. So we think that the helium-2 line is tracking the optical X-ray UV continuum. So it can be associated with the soft axis spectral variation. So yeah. So this is a work in progress to understand what has caused the multi-wavelength flaring. So since the optical and UV vary more than the X-rays, we rule out the X-ray to optical UV reprocessing models. And we see a strong change in the shape of the soft axis, which can be modeled with the warm comptonization. Now, again, we know that the soft, the nature of the soft axis is still not very well known, and it can be either modeled with warm comptonization or models having ionized disk reflections. But yeah, so with the SED, again, there is a decrease in the L bolometric to L Eddington ratio by a factor of 3 to 4, and the warm and hot corona regions migrated to a large radii as flare subsides. So the value of KT is higher than 0.5 kilo electron volts during the flare for the soft axis. So Yes, these are like things that we are still probing, like what could have driven this flare? Could it be a QPE? Is there any other models that we can consider, like this instability models? What has caused the helium-2 line to disappear? Why, like, what's the connection between, you know, the soft excess spectral change and the disappearing helium-2 line? So yeah. I end this talk and I'm open for questions.
Questions?
So in the case of fitting the soft excess with a warm corona model, have you estimated what's the optical depth in that case for the corona?
Estimated what?
The optical depth.
We got some values. I don't have them right now, but like this is still an initial fit, and I still need to properly like fit them and get those values. Yeah, sorry, I don't have it.
If there are questions online, just speak up. I cannot see Zoom. Okay.
Daniel Stern here. I was wondering if there's any radio information on that source that you could talk about.
Radio?
Yeah.
Oh, yes. We tried to look if there is any radio component, but so far we don't know. Yes.
Thank you.
Okay, let's thank speaker again. We have one last talk from Johan. Can you hear us?
Yes. Can you hear me well?
Can you put on Zoom?
Can you hear me well, Ilaria?
A bit soft. One moment, Johan, they're setting up. Okay, go ahead.
Thank you, Ilaria. Hello, everyone. My name is Yuhan Yao. I'm a graduate student at Caltech. It's my great pleasure to talk to you about tidal disruption events today. I'll focus on their X-ray properties and highlight some recent results from NuSTAR. So first, I want to show an artist's conception of what is a tidal disruption event. Here, the black dot is a massive black hole in the center of a galaxy. The blue circle is a star moving towards the black hole. As the star gets too close to the massive black hole, it will be tidally disrupted and evolves into an elongated stream. Half of the stellar stream will remain bound to the black hole. They go back and get accreted, forming an accretion disk. The first theoretical prediction for the TDE phenomena is presented by Martin Rees in 1988. He calculated that within the tidal radius, where the star's self-gravity equals to the set tidal force, the star will be fully disrupted. So roughly speaking, for a sun-like star, the tidal radius is roughly half of an AU. We need the tidal radius to be larger than the Schwarzschild radius. Otherwise, the star will be eaten by the black hole directly, and we see no EM radiation. And this sets the black hole mass to be less than 10 to the 8 solar masses in order to produce a TDE. So TDEs are really sitting in the center of a wide range of high energy phenomena. They provide an ideal laboratory to study the real-time formation of an accretion disk. Because the expected stellar debris mass fallback rate is above Eddington limit at early time, we can use TDEs to study super Eddington accretion. A small fraction of TDEs launch relativistic jets. Those jets turn out to be very different from what we have seen in gamma ray bursts, X-ray binaries, and blazars. So it becomes very interesting to study the geometry and the structure of the jet itself, which can improve our understanding of highly spinning black holes with magnetically arrested accretion disk. TDEs have also been proposed as unique probes of the quiescent black hole population. If we understand the selection function well enough, we can use the TDE demographics to measure the black hole mass function down to the intermediate mass black hole regime. By modeling the radial synchrotron emission, we can measure the matter density as a function of distance, and such a matter density profile bears some information about the accretion history of the host galaxy. Just recently, a X-cube PeV neutrino was associated with an optically discovered TDE, so they are also important multi-messenger sources. And finally, TDEs are related to extreme mass ratio inspirers, or IMRIs. Those are stellar mass compact objects orbiting supermassive black holes. We have already found lots of TDEs, and numerous IMRIs will be discovered by the next generation gravitational wave detector, LISA. So the vast majority of TDEs are not associated with any on-axis relativistic jets. Some of them are detected in the soft X-ray, where we think the X-ray emission is from the inner regions of an accretion disk. Some of them are detected in the UV optical band, where the UV optical emission is consistent with a black body with much larger radiant and lower temperatures than the soft X-ray component. We think that the UV optical is coming from a reprocessing layer, but the nature of this reprocessing layer is very actively debated. Popular scenarios invoke either a radiation-driven disk wind or a stream-stream self-collision shock. So here on the top, I'm showing a RMHD simulation of a super attention disk in the TDE context. Here, the strong radiation pressure puffs up the disk vertically, so we have a geometrically thick disk. A large fraction of the gas is lost in the form of a fast wind or outflow. Such a wind is optically thick, so it can reprocess some of the disk X-ray emission into the UV and optical. The bottom shows a scenario where the infalling stellar stream collide with the returning stellar stream. Such a collision can be very powerful, and it can drive a strong outflow, which can also serve as the reprocessing layer. The sample of TDEs associated with on-axis relativistic jet is very small, only 4 events. 3 of them were discovered by the First Alert telescope on the SWIFT satellite, and 1 is recently discovered by optical sky surveys. This one was AT 2022 CMC, which I will introduce in more details later. So among the 4 jetted events, SWIFT J6044 was the most well studied. Its X-ray-like curve is shown here on the blue. You can see that the early time X-ray luminosity is much above the Eddington limit, even for a 10 to the 8 solar mass black hole. And the variability is very extreme on very short timescales. So this indicates that the X-ray emission is from internal dissipation within a jet, presumably launched from the inner accretion disk surrounding a rapidly spinning black hole. Here is the early time ICD of J1644. Buisson et al. Proposed that maybe the X-ray is powered by synchrotron emission produced by relativistic electrons in the jet. Here to produce this very steep X-ray to optical spectral slope, we need the jet to be magnetically dominated and be starved of low energy electrons. This is very different from what we see in blazars. And the Fermi high energy non-detection further suggests that the Compton self-Compton component is suppressed by gamma pair production. So this is only one of the few possible explanations. Some other authors also argue that maybe the X-ray is powered by external inverse Compton scattering. So the X-ray emission mechanism is really an open question in the TDE field. But the key here is that you can see that those jetted TDEs are really bright hard X-ray transients. So they are excellent, rare, fascinating objects to be followed up with NuSTAR. And the last point I want to highlight for those jetted TDEs is that in both J1644 and J2058, we observe a sudden drop of X-ray flux at roughly 1 year after the discovery. So this has been explained as a shut off of the relativistic jet when the mass accretion rate drops from super Eddington to sub Eddington. The disk transitions from being geometrically thick to being thin and enters into a thermally dominated state. and such a thin disk is neither observed nor theoretically expected to be able to hold powerful jets. In recent years, we are really entering into a golden era of TDE studies, because even 5 years ago, there were only 3 dozens of TDE candidates selected from a wide range of observatories. The vast majority of them have little multi-wavelength coverage and very sparse light curves. A step change in the TDE discovery rate was made possible by the Zwicky transient facility. So ZTF uses the Palomar 48-inch telescope to scan the whole northern sky with its very wide field of view camera. In phase 1 of ZTF, there is a 3-day cadence out-sky survey with the G and R bands. And starting in phase 2, the out-sky cadence has been further shortened to 2 days. Also, starting from ZTF phase 2, we are trying to make sure that we classify all TDE candidates with a peak G-band magnitude greater than 19.5. So this systematically selected sample will eventually be very useful to assist population studies and to measure the optical luminosity function of TDEs. In the X-ray sky, TDEs were first identified by the ROSET out-sky survey more than 30 years ago. Starting from the early 2020 to earlier this year, the eROSITA telescope on the SRG satellite has been the most prolific X-ray discoverers of TDEs. So in a recent paper, we presented 13 eROSITA TDEs selected from the first year of operation from the Russian half of the sky. And what we found is that those X-ray selected TDEs are relatively faint in the optical. So I have always been very curious about the X-ray light curves of TDEs, because if we only look into the optical, the light curves is more or less homogeneous. They typically rise in a month and then decay in a few months. But if we look at the X-ray light curve, we can really see a diversity. A few of them show this delayed X-ray brightening at late time, and we think that might be caused by delayed formation of an accretion flow or some obscuration at early time. Some events show this type of very fast X-ray flares on the timescale of a few days, and people believe maybe this is associated with patchy obscuration. The neutrino emitter 19DSG showed this early time fast fading X-ray light curve, and it's not clear what's causing that. And a few events only show this very deep upper limits at early time. So understanding the interplay between the optical and the X-ray emission may hold the key in deciphering what is powering those two components. Among all non-jetted TDEs in the literature, Assassin 14 Li was the best studied event because it's both nearby and very X-ray bright. Miller et al. Reported the detection of narrow absorption lines blue shifted by a few hundred kilometers per second in early time XM Newton and Chandra grating spectroscopy. On the other hand, Carroll et al. Focused on the continuum shape in the XM data obtained both at early and late times. And what the authors find is that in the early time XMM data, there appears to be a very broad absorption feature that can be attributed to oxygen 8, blue shifted by 0.2 C. So these discoveries have been attributed to absorptions in a super Eddington radiation-driven outflow, where the low velocity features might be coming from a region that's much further from the black hole than the high velocity features. So Assassin 14 Li was a TDE that remains extremely soft throughout the whole evolution. Although the vast majority of TDEs are similarly soft at early time, in roughly half of the eROSITA TDEs, we do observe a significant spectral hardening at the 6-month survey cadence. And this spectral hardening might have something to do with the accretion at different regimes. So here I'm showing the expected stellar debris mass fallback rate as a function of time. You can see that it spans several orders of magnitude. So we do expect that TDEs will go through a wide range of mass accretion rate in its evolution. So we can ask how often and on what time scales does the spectral hardening happens in TDEs, and why it happens? Is it because of the formation of a magnetically dominated corona? And if so, how would the corona evolve together with the accretion flow. And we can further ask, for those TDEs that do turn harder at later times, how would the X-ray spectrum look? Are we still able to detect absorption features as we have seen in assassin 14 Li? Or how about emission features? Are we able to see the corona emission reflected off the accretion disk, giving rise to the iron emission line and the Compton hump? So all of those open questions naturally motivate us to look into TDEs in the hard X-ray band with NuSTAR. So I'm happy to report that recently we have been able to study the hard X-ray emission in the non-jetted TDE in much greater details. This TDE is a AT2021 EHB, which was discovered by ZTF in March of 2021. As the third closest TDE ever discovered in the optical, its peak X-ray flux has reached 1 millicrep, which is even brighter than assassin 14 Li. And because it was so bright, we were able to study it with many X-ray telescopes. So here I'm going to show a small movie of 21 EHB's multiwavelength evolution. The source was classified as a TDE based on its slow rise time and the strong UV detection. Prior to the optical peak, there was no X-ray detection. After that, the source went into sun constraint. After it comes back to the sun, we immediately trigger SWIFT and get a bright X-ray detection. The X-ray is even brightening, so we triggered XM Newton telescope. As the X-ray continues to brighten, the hardness ratio also significantly increased. At a certain point, it was bright enough to be observed with NuSTAR, so I triggered my TOO program and also asked for a longer DDT observation. In January of this year, the X-ray flux suddenly dropped by a factor of 10. At the same time, the hardness ratio also significantly decreased. In March of this year, the X-ray flux further dropped by a factor of 6. And as of right now, the source has gone behind the sun again, and we are waiting for it to come back. So because we have this good set of multi-wavelength coverage from optical near UV and X-ray energies, we can estimate the bolometric luminosity. So here, if I assume that the far UV ICD shape is a power law connecting the near UV and the soft X-ray bands, then this is the derived bolometric luminosity. And here it's how it scales with the Eddington luminosity. So you can see that the Eddington ratio remains below 10% all the time. But the caveat is that this does not necessarily mean that the mass accretion rate is in the sub-Eddington regime, because we actually do not know how the EUV spectrum look like. Some of the recent RMHD simulations of TDEs show that maybe the bulk of the radiation in TDEs peaks in the extreme UV band. So the estimated bolometric luminosity can be considered as some lower limits. A very peculiar property of this source you might have noticed is that the X-ray spectrum changes from being soft to being hard and then soft again. This is the first time that such a spectral evolution is observed in a TDE. And to look at it in more details, I have divided the multi-wavelength evolution into 5 different phases, from A, B, C, D to E. And here is the typical optical to X-ray SCD in each of the different phases. So from the multi-wavelength evolution, we propose the following interpretation. From phase A to phase C, the stellar debris is in a very complex hydrodynamic structure. During the process that it circularized to form an accretion disk, the inner portions of the accretion flow gets closer to ISCO, such that the soft X-ray, which traces thermal emission from the inner accretion flow, gets stronger. At the same time, a magnetically dominated corona forms, such that we start to see some of the non-thermal emission from the corona. From phase C to phase D, MRI further amplifies B field, such that there are more soft X-ray photons being inverse Compton scattered, and we see that the non-thermal component brightens. From phase D to phase E, at the same time of the X-ray spectral softening, we observe a sudden decline of X-ray flux by a factor of 10. This happens at roughly 1 year after the discovery. And the timescale of 1 year is very interesting because first, it is consistent with the timescale when we expect the stellar debris mass fallback rate to transition from being super Eddington to being sub Eddington. And second, this timescale is also similar to when we observe the jet shuts off in those jetted TDEs. So we propose that this transition is triggered by a thermoviscous instability in the inner accretion flow, where the disk transitions from a radiation pressure dominated thick disk to a gas pressure dominated thin disk. So next, I want to focus on the hard X-ray spectrum obtained in phase D, because this is only the second time that we observe a prominent non-thermal component in a non-jetted TDE. Before 21 EHB, 2018 FYK was the only one that shows a prominent hard component at a certain time in its evolution. This source is very interesting on its own, but it's a little further away to be looked with NuSTAR. In 21 EHB, we clearly detected 30 keV X-ray photons in the NuSTAR spectrum. And this detection alone bears some information about the system, because in the TDE scenario, the hard X-ray photon needs to get out of a very complex hydrodynamic structure. Suppose that the photon needs to travel through a gas slab of Thomson optical depth tau. It will undergo tau squared times electron scattering. And in each Compton scattering, it will lose a fraction E gamma over MEC square of its total energy. So in order to have 30 keV X-ray photons, we need the Thomson optical depth along certain line of sights to be less than 4. But by modeling the UV and optical emission, we know that the UV optical emitting region must be optically thick up to 10 to the 14 centimeters. So taken together, our observation favors a highly non-spherical system. And this is not all of the story. We can learn more about the system by carefully modeling the NICER and NuSTAR spectrum. So here is the result if I only use a combination of multicolored disk and inverse Compton scattering. You can see that this is not a very good fit. There is strong residuals from 2 keV all the way up to 30 keV. So we tried 2 approaches to improve the fit. The first is to add absorption features, and the second is to add disk reflection features. So here is the result of adding absorption. The ZXI PCF model considers partial covering of some ionized worm absorbers with a certain column density and a certain velocity. You can see that this is maybe an acceptable fit, but there seems to be some systematics between 9 and 12 keV where the NuSTAR residual is all negative. On the other hand, the disk reflection model does a much better job. At first, it came to me as a surprise that disk reflection can do such a good job, because what we are much more familiar with is the strong iron emission line and the strong Compton hump. Instead, what we have here is a very broad iron profile. And this is mainly determined by the high ionization of the accretion disk. So here the black line shows the best fit model spectrum. And you can see that the best fit log size is as high as 4, whereas in other AGNs, the value is typically lower. So as we have postulated before, in the hard state, the TDE is in a super Eddington accretion state. So maybe here the disk surface where the optical depth equals to 1 is much further away from the midplane, and the ionizing flux it receives is much higher. Another parameter that we can constrain relatively well is the inclination. This is mainly relied on the general shape of the continuum. Unfortunately, at such a high ionization state, the fit is very insensitive to the spin parameter. But nevertheless, I think the NuSTAR's detection of relativistic disk reflection features corroborates the existence of a corona and motivates us to look in the hard X-ray band of future TDEs. The last minute of this talk, I want to briefly report on the recently discovered jetted TDE AT2022CMC. This source was first discovered by CTF in February of this year as a fast-fading optical transient. It is actually the first non-jetted TDE discovered ever since NuSTAR was launched, and the highest Z redshift jetted TDE we ever know. So of course, it has received lots of attention from major X-ray facilities. And here I just want to emphasize that the rapid response time of NuSTAR and the flexible scheduling have really allowed us to obtain a set of joint observations together with the soft X-ray facilities. And it is by the NuSTAR observation that we are able to tell that the X-ray spectrum is not a single power law. Instead, it is a double power law, and the spectral shape remains relatively stable throughout the evolution. There are ongoing efforts to investigate how this set of observation can help us to constrain the jet properties. So in summary, I think the studies of 21 EHB and 2022 CMC have really opened up an exciting avenue of finding these exciting TDs in optical synoptic sky surveys and following them up with NuSTAR. As an observer, I think it's very helpful to develop systematic follow-up strategies, to always look into the data very promptly and carefully, and to be a bit adventurous in planning the follow-up observations. So I wish NuSTAR a happy 10 years birthday, and I'm sure more exciting TDE science from NuSTAR is just around the corner. Thank you for listening, and I'm happy to take any questions.
Thank you, Johan. Questions? On Slack? Can someone? I hear there's a question on Slack. Maybe if the person is on Zoom, can just speak up and ask the question.
Kaya.
Okay. Go ahead.
Who is, I have a question, but do you hear me?
Yes.
Okay, okay, great. I'm Shwelem Bauman, and I had a very simple question actually. How exactly do you differentiate? Do you have a way of differentiating, looking at your observations, optical X-ray comparisons? Can you differentiate for what is being tidally disrupted?
Being tidally disrupted compared with AGNs or some other transients?
Oh yeah, I mean, you're talking about the tidal disruption event, right? So
yes.
Something is disrupting, right? Tidally?
Yes,
okay.
So
okay. So can you, I mean, is this a star or this a binary or this is a neutron star? I mean, am I getting this right or wrong in the sense of?
Yes, so you are asking about the nature of the disrupted object.
Exactly.
I see. Yeah, so it's a relatively hard question. So in the case of 21 EHB, we know that the massive black hole mass is around 10 to the 7 solar mass, and that sets the minimum mass of the disrupted star to be around 0.3, 0.4 solar masses. So it cannot be a white dwarf or neutron star or black hole. But how massive it is for a star, we are actually not able to tell because we are not sure if all of the star is disrupted and what fraction of the star is get accreted. Initially, people think by looking into the optical spectrum, sometimes we observe helium lines and sometimes we observe hydrogen lines. And maybe this is telling us something about the composition of the disrupted star. But I think more recent simulations show that this is mainly an optical depth effect instead of telling us that what the composition is for the star. So yeah, this is a hard question, I think. Mm-hmm.
Okay, thanks. So this is something to be explored as I see. Okay, thank you.
Yes, mm-hmm. You're welcome.
Hi, can I ask you a question?
Sure.
Yeah, so I'm interested in this TD detected by IceCube for the neutrinos. So I'm wondering if this was totally unexpected in the community, and what's the physical mechanism to produce the neutrinos? Like in the hadronic interactions, what's the target? You know, do you require relativistic outflow or jet?
So in 19 DSG, the source associated with the IceCube I think it does have a more or less subrelativistic outflow detected in the radial band. And we do, because the first neutrino is associated with a blazar, we do expect some massive black hole accretion events to be able to produce neutrino. But the exact emission process, I'm not very familiar with that.
Okay, thank you.
You're welcome.
I have a question for you, Johan. The absorption feature that Miller and Erin found, so they're only been observed in this one object. Is that because it was bright enough and the other ones are not bright enough to detect this kind of absorption features, or is it just special about this object?
Exactly, because it's bright enough. The grating spectroscopy is very hard. You need it to be at least 1 millicrab to do this kind of job. And the vast majority of TDEs are just not that bright or nearby. Mm-hmm.
And what about the last object that you described? That one was bright enough, right? But you didn't see this kind of absorption features?
You mean 2022 CMC or 21 EHB?
The one with the reflection spectrum.
Oh, this one. So I know that John has obtained a few grating spectra using XM Newton and Chandra, and in the ATEL that was reported, I think it's those two ATELs, he does reported the detection of some absorption features. But my data does not have enough resolution to be able to tell if there's absorption features in NICER and NuSTAR. So we just need to look into the ATELs or maybe wait for another publication from his team.
Okay, thank you.
Mm-hmm.
Leo, can I ask 2 questions?
Sure.
Yeah. Could you please go back to the line curves you show for the jetted TDEs? I'm just wondering how you calculate the luminosity here, because you're saying that the X-rays come from the jet, which is beamed. And how do you calculate this luminosity? And how do we know this is Eddington? That's basically my question, because the emission is basically, is beamed.
Yes, so this is just showing the isotropic equivalent luminosity in this X-ray band, and we do know that it's beamed, but we are not sure what the beaming factor is, but just the apparent isotropic equivalent luminosity is super Eddington.
Oh, okay, I see.
Mm-hmm.
Do you have an idea about a beaming effect, like a general one, or from series or either observations? I don't know how to measure this, but I'm just asking.
So I guess we can constrain this using the Lorentz factor, maybe derived from the forward shock, and that is typically around 3, inferred from radio observations.
I see.
But I'm actually not sure, because the X-ray is thought to be coming from a much smaller region than the radio forward shock.
Yeah.
So,
yeah, it's good to see that. Okay, it's isotropic. Oh, it's written there. Sorry, I didn't notice that.
No worries.
And my second question is for your last source. You show the power law component starts showing up, and you have some. Yes, so that one. Do you